Maybe is where we not.
Vou trocar. Se eu não ficar aqui, você.
Bom dia a todos. Obrigado pela presença de todos. É uma oportunidade aí ímpar, né, para vocês, para mim também, receber 4 colegas aí do exterior, né? 4 colegas que são referência nas áreas de trabalho que a gente trabalha, obviamente eles. Então é uma oportunidade muito boa para vocês terem contato com eles e fazerem perguntas, fiquem à vontade. Aquelas pessoas que tiverem dificuldade em falar inglês, pode falar em português, a gente traduz para eles, tá? Mas o mais importante aqui, além do seminário, vocês verem o que eles estão fazendo no exterior, vocês terem contato também com os pesquisadores de fora do país, né, que são referências nas áreas que eles trabalham. I will introduce you guys in Portuguese, and then I will change to English, okay? I swear that I will say exactly what you sent to me. Então, a primeira palestra que nós vamos ter hoje, we invite Professor Gael Kung, Professor Frank Osterloh. Gael Kung is from University of Connecticut in United States. Professor Frank Osterloh is from University of California in Davis. And Professor Eva Hammer is from University of Ottawa in Canada. And Professor Christopher Cahill is from the George Washington University in Washington, USA also. So in the morning we are going to have 2 talks from Professor Gael and Professor Eva. And after lunch at 2 p.m., we are going to have 2 more talks from Professor Frank and Professor Christopher. So I hope you guys enjoy it. And as I said, everybody can if you wish to have a question in Portuguese, you can do it. We try to translate the best we can to the professor. Okay. So let me introduce Professor Gael. Professor Gael, he was born in France. He received engineering degree from the Chimie Paris Tech and master degree from the University Pierre Marie Curie, now in Sorbonne, in Paris, also France. Then Gael moved to the US in 2009, and he received his PhD degree in 2013 with Professor Guy Bertrand, and he started PhD at University of California in Riverside. Then he moved to University of California in San Diego, and he worked with mesoionic carbons. He then moved to Caltech for a postdoc with Professor Jonas Peters, and he worked with low valent iron complex and nitrogen fixation. Professor Gael started his independent career at the University of Connecticut in 2016, working on the coordination mechanics of lantanides and transition metal, applying them for circularly polarized luminescence. In last year, in 2023, he was promoted to associate professor with tenure in University of Connecticut. So, Professor Gael is a young professor, but is already a reference in circularly polarized luminescence in the world. And I have the pleasure to stay with him 20 days ago at the University of Connecticut. So Gael is helping us a lot on this field. So thank you, Gael, for coming. And we are excited to see what I have to say, and the stage is yours.
Okay,
Thank you, Gael.
thank you very much. Don't clap before, clap in the end. Thank you everybody for coming early. I'm very excited to be here. It's my first time passing the equator going south, so it's very exciting to be here. Today I'm going to talk to you about some circularly polarized luminescence and in the F block, but the whole F block, so you'll see some cool things in the end. But before I go into all of the chemistry, I wanted to give you a good introduction to put everybody on the same page. Some of you work with circularly polarized luminescence, but not all of you, so I wanted to start there. So my group is very motivated with chirality and understanding chirality, and that's probably because we are chiral. We are all chiral. You know, for example, this is DNA. I have one here. It's going to be easier. And DNA is a double helix, so you can have two non-superimposable mirror images of DNA. So it's chiral. And what is kind of cool about DNA is you can only find one enantiomer of DNA. On life on Earth is only right-handed DNA. You cannot find left-handed DNA naturally. And that's a good question, and I'll come back in one minute. At the molecular level, you can find molecules in nature that exist at both enantiomers, and there are subtleties in their properties. For example, this is a molecule that is called carbone. It's also a molecule that exists in two different mirror images, and one of them smells like mint, and the other one smells like caraway seeds, kind of like dirt. So it's kind of a subtle difference on the smell, but that tells you that the chirality is important for the molecule. Properties can be a lot different. So for example, methamphetamine exists as two different enantiomers. One of the enantiomers is the active ingredient in the drug. It's an inhaler. So if the winter gets very cold, you can have a stuffy nose, and you can sniff this, and your nose you can breathe better if you sniff this drug. The other enantiomer of methamphetamine, you should not sniff this, because this is crystal meth, right? And so instead of decongesting your nose, it will just make your nose disappear, right? So chirality is really important. And so coming back to why is life on Earth only 1 enantiomer of chirality? This is a big question in the scientific community. There is still no big answer. And when I was reading about this, because I like this topic, I saw one hypothesis that says that circularly polarized light that you find in nebulae in like outer space could be at the origin of the homochirality of biological molecules. So my question was, okay, what is circularly polarized light? What can we do with this? So let's talk about the polarization of light. As you know, most of the light from light bulb or the sun is non-polarized, so it propagates in random directions. So that looks like this. All of the wave orientation exists. And if you were to look at it coming at you, you'd see something like this, something with like all of the random directions. You may have heard of linearly polarized light. This is light that you can use in sunglasses or things like this, like filters. And at that point, you only select one of the directions. So if you look at the light coming at you, it looks like this. Linear, it can be at any angle, but it's always just a line. One thing that people are less familiar with is circularly polarized light. So this is light that instead of propagating through a line, it now propagates through a helix path. And like I've shown you, helix in DNA can be right-handed or left-handed. So you can have right-handed circularly polarized light or left-handed circularly polarized light. And if your eyes were equipped to see this, you would see something like this, light that comes at you as a circle, but then that turns clockwise or counterclockwise depending on what handedness it is. And that you could see them as 2 non-superimposable waves of light. So these can be simplified in my head as chiral light, or light with an added chiroptical information. And that you could think about using now that chiroptical information for something, and people think that that chiroptical information was transferred to the first amino acid, and then that has generated us as just being right-handed DNA. But as you can see here, I've shown you how to make circularly polarized light. You generate linearly polarized light, you filter half of your light, and then you transform it into circularly polarized light. And the use of these filters is really inefficient to use that chiral light, but using the extra information would be helpful. So that led us to ask ourselves 2 questions. One is, can the CP light be emitted directly without using the filters, without losing energy? And if that would be the case, that would be called circularly polarized luminescence, or CPL. And then at this point, can that CPL be useful? So to answer that question, we like to take inspiration from nature. You can find animals that have circularly polarized light interacting with them. So this is a beetle that you find in Southwest America, North Mexico. And you can see that here is 2 pictures of the same beetle, but they're taken with circularly polarized lenses. And so one is dark, and the green that you see is circularly polarized light that's coming out of this beetle. But this beetle is cheating. It's not emitting the light, it's just reflecting the light and adding the chiral information. To see real emission, you need to find other animals. So this firefly here that we can find in Connecticut emits circularly polarized light from its tail. Another animal, this shrimp here, has a tail that emits circularly polarized light. So here you see the same concept, 2 pictures of the same tail, but like with the 2 different lenses, and you can really see that this is giving you bright red circularly polarized light. And what's really cool about this shrimp is that the people that have done all of the studies that I cite there, they've done studies on the biology and behavior on these shrimps. So they've seen that the eyes of the shrimps can detect the difference between the left and right circularly polarized light. And in the behavior study, they are responsive to one type of light versus the other type of light. The hypothesis is that they're using this for species recognition, so mating, so survival, but also because their eyes are kind of more sensitive to a different type of light that helps them navigate in turbid water better. So that kind of answers on two questions, right? Circularly polarized light can be emitted directly. You have examples here. And CP light, circularly polarized luminescence, can be useful for these shrimps. So what can we use it for us humans? Well, because we're looking at light emission, most of the things you'll think about are these visible range light, but I'm going to also talk to you about more longer wavelengths in the near infrared. So in visible light, circularly polarized light is at the core of 3D technologies nowadays. If you've been to 3D movie theaters and put the polarized glasses, you're looking at circularly polarized light. But if you've done that, you've always gone to a room that has a very big screen and very dark. That's because of the energy efficiency issue. So if we can use circularly polarized emitters directly, we could miniaturize this and maybe get 3D cell phones in the future. Some people are thinking about anti-counterfeiting. So this is a $20 bill in the US, and if you put under UV light, you get a green fluorescent band that tells you that it's presumably a real money. But here you can clearly see it's very easy to get to UV light, so you can know where to put a green band. And if you do lanthanide luminescence, you may recognize this looks like terbium. So you could put a little terbium in a $20 bill and it could look real. But now if you have extra chiroptical information that nobody can see with the naked eye, you can make this a little more secure. There are also some cool applications of sensing and asymmetry catalysis, but I won't talk too much about this. Now, if you move to longer wavelength in biological range, this is a region in the spectrum that is transparent to near-infrared light in your body. So you can enhance biological sensing because all of the things in your body is chiral, almost all of it. And then now, what is exciting to us is to move into longer wavelengths. So now in this near-infrared region, this is where most of our information is transmitted in the form of light traveling through fiber optics. So now, if we think about transporting not just normal light, but chiral light that has extra information, you could maybe develop what people are thinking about for quantum computing or quantum networks, because you have more information per unit of light now with what we're trying to do. And so when we started this work, we did a lot in the visible, but there was really nothing in the near infrared, so we were very interested into going into that region, so that's where I'm focusing on today. And what is really good to make circularly polarized light is lanthanide. And I'll come back to exactly why before, but to get light out of the lanthanides, many of you work with this, it's not as tricky. So I want to introduce you to how we can get light out of our lanthanides. But before I go there, let's put everybody on the same page and talk about just how do we get light out of a molecule. So very simply, typically you have a ground state and an excited state, and then you excite your molecule with light or electrical current or whatever, and you populate that excited state. And then it can come back down and emit some light, and that's your typical fluorescence. Sometimes you have an accessible triplet state, you will do an intersystem crossing, and then emit from the triplet state, which is forbidden, and that's called phosphorescence with longer lifetimes. So that's kind of very simple point of view. You can think that for lanthanides it's exactly the same. You have ground state, excited state, you absorb, you emit, same story. But these states, they are not simple singlet or triplet state, they are F to F, they are F-derived orbitals. That means that the transition between these orbitals are F to F transitions, which are forbidden by selection. That means that the absorption is a lot less probable, meaning it's very difficult to populate that excited state, so you cannot get a lot of light. So you typically have weak emission from the lanthanides. A good way around this is called the antenna effect or sensitization. And what you do is, you know that your objective is to populate that F star to allow it to emit light, but you cannot do it directly from the F ground state. What you're going to do is you're going to append a chromophore to it. It can be an organic molecule, it can be a metal, it can be anything you want. That has now an allowed absorption that will populate a singlet state, and then through a series of energy transfer, you can populate that F star and get you to get light out of your lanthanide. So simple picture, but we're not just interested in normal light, we're interested in chiral light. So how do we get chiral light coming out of our molecule? We like to do coordination chemistry of small molecules. So if you think about a chiral lanthanide, like chiral light coming out of a lanthanide complex, you will think chiral complex. And because we need that antenna effect, it's very versatile to us to think about something to build with our molecule, because we can impart chirality in 2 points. The first point is we can have chirality at the metal itself. If you've taken inorganic chemistry, you remember that propeller, delta, or lambda chirality. So that's 1 point of chirality we can introduce, or we can just have a chiral ligand, or we can combine both at the same time. So that's what we tried to do. We were very interested in thinking about a system that would have high symmetry and that would combine chirality at the ligand and chirality at the metal. So we looked at the literature, and this, oops, sorry, I lost my finger. This here is a very well-known complex in the literature that has an axially chiral ligand. There is restricted rotation around that CC bond, so you cannot interconvert the 2 wings here. And upon coordination onto the metal, it selectively will get a preferential delta or lambda at the metal itself. So that was perfect for us to start to investigate. But these are very well known and very well studied for like 40 years. And in the literature, almost everybody said this is not luminescent. And so if you look with work with luminescent material, that's kind of a bad news if you read that in the literature. But we recognized fairly quickly that maybe people were just not looking in the right region, because luminescence, the best spectroscopy to see something is eyeball spectroscopy. So if you cannot see it, you think it's not there. But if you look at the ligand here, this is a pretty conjugated ligand. That means that the singlet and triplet states are very low in energy, and visible emitting lanthanides are going to be higher in energy here. You cannot transfer energy upwards, so of course you cannot see light. So to see light, I've shown you, you need to have that singlet and triplet above the emissive state. But we thought maybe people didn't look carefully. Maybe instead of using a visible lanthanide, you need to use something that emits at lower energy, so you can have that cascade down in energy. And then if you pick the right lanthanide, you should get light, and then maybe chiral light at this point. So we picked the lanthanides that emit in the near infrared. First one is ytterbium. This is an emission spectrum, so intensity of light depending on the wavelength. And you see the very sharp peaks characteristic of an ytterbium emission, about 970 nanometers here. We also tried neodymium that emits in different regions, but mostly centered in the near infrared 1 window, and also erbium that emits in the near infrared 2 region at 1550 nanometers. This is a little misleading because this is normalized emission. The ytterbium is the most intense of these 3. Okay, so we have light. This is cool, but as I told you, we're interested in chiral light. So do we have chiral light with this? If you haven't seen CPL plots, I'm going to introduce how we plot them usually here. So this, in the background, we like to have the total luminescence just as a reference. And we are going to superimpose the CPL spectrum. And so here is an example of a CPL spectrum. What you're looking at is a difference of intensity between the left circularly polarized light and the right circularly polarized light. So if these 2 are equal, that means you don't have CPL. That would be like this horizontal line here. But anytime you have a peak that deviates from that line, that means you have CPL. So that was really exciting to us to see that we had CPL with that compound. What is also cool that we have access in the lab is the enantiomer complex. And you know that enantiomers are mirror image of each other. So if you take the spectrum of the enantiomer, you get the mirror image spectrum, which makes it a pretty graph, but also it helps us make sure that this is not an artifact, that it's really coming from our complex. Okay, so we have chiral light coming out of our complex. How do we know how good or bad it is compared to the literature? So let me spend a minute introducing you to the metrics that allows us to quantify circularly polarized luminescence, and then we'll be able to compare what a molecule does. So this is how we quantify it. One metric is called the dissymmetry factor, or GLUM. here, and it basically just tells you how polarized or how chiral your light is. And you measure it experimentally by looking at the difference of intensity over the sum of the intensity. So that's why when I presented the spectrum, I had the overlay of the sum and the difference, so you can see the two at the same time. If you solve this equation, you will see that you can only go from -2 to +2, centering at 0. 0 obviously is when these two values are equal, no CPL. -2 is 100% right CPL, and +2 100% left CPL. And in the literature nowadays, it kind of looks like this. So red is bad, green is good. Obviously, when you have no CPL, it's bad, and when you have high numbers, it is good. The best, actually, I need to edit this. This is no longer the best, but almost close to the best. Molecular example is a europium-based complex that has this camphor-derived ACAC ligand, and it has a dissymmetry factor of almost 1.4. So it's actually really, really good. And you could think that the problem is solved, but that's actually a little misleading. There are only maybe 5 to 10 examples above 0.5 in the symmetry factor. So let me zoom in here, and you'll see that I'm going to switch to a log scale to really show you how challenging it is to get chiral light. So obviously 0 is still bad, but 10 to the -3, there's a lot of literature nowadays that calls this strong circularly polarized luminescence. When you're 3 orders of magnitude lower than the theoretical maximum here, I don't call this strong, right? But it tells you how challenging it is in the field that even a little bit of polarization is like an achievement. And of course, if you go to 10 to the -2, 10 to the -1, you get to better and better now. Another way I like to present this is not just on the raw scale of good or bad, it is on the number of examples that you can find in the literature. And so obviously you find a lot into the 10 to the -3, and here you can see above 0.5, there is almost nothing. Okay, so that's one metric. It tells you how chiral your light is, but when you have a light emitter, this light bulb could give me 100% chiral, but there is no light coming out of it, so that would be completely useless. So I need to know how bright the light comes out of my emitter. So recently, this metric has been also introduced in the literature. It's called CPL brightness, and tells you how bright and also how chiral your light is. And if you do fluorescence, you recognize brightness is a product of molar absorptivity and quantum yield, except here you're going to also multiply the dissymmetry factor for an idea of how chiral your light is. And because you have molar absorptivity in that equation, the higher this number, the better it's going to be. So you want to go as high as possible. But just to help you calibrate yourself in the literature, right now the lanthanides are about a few hundred per molar per centimeter, and the transition metals are a few tens of per molar per centimeter. So it's not super good. Okay, so now that you know how to quantify this, how does our ytterbium complex compare? Well, the dissymmetry factor is not too bad. We're at almost 0.2, and the brightness is, again, in the low 100, like all of the lanthanides, but it's actually pretty good for ytterbium, and at the time of this publication, that was 2 orders of magnitude better than the previous best. Now, the best is about 800 per molar per centimeter, so still in that range. Okay, so ytterbium was very cool, but we were very interested in that near-infrared 2 region for the telecom application and the quantum network that I have told you. So here is the erbium spectrum. So in pink is the total luminescence, and then you can see the mirror image non-zero CPL from the 2 enantiomers here. And in terms of metrics, we're actually really good. We're getting almost 0.5 here. The brightness is a little lower, but I'm going to touch on that with the subsequent work that we've done. But what was really exciting to us was to see that the maximum polarization here is also exactly at 1550 nanometers, which is where the transmission loss in our current fiber optics is very low. And what it means is that what we can do with a little bit of engineering is put our emitter in a device and start transmitting chiral light in our current fiber optic infrastructure without having to rebuild it. And so this work was significant not only because it was the first example of erbium CPL, but also it's the first time we could see CPL in the telecom C-band. And so maybe our first step towards quantum network using polarized photons. And so that led us a quest to make this more practical. And to make this more practical, we need more chirality in our light and more brightness. And so these are the two metrics that we try now to push up. And so how to do this? The symmetry factor, I've shown you how we do it experimentally. Theoretically, it looks like this. So it is linked to an electric dipole and a magnetic dipole transition moment of your luminescent transition and the angle between them. And so what you need to do is to manipulate dipole transition moments to try to get to a better number. I say it's currently hard to predict because to us, it's very easy to visualize an electric dipole transition moment. It's like a minus and plus charge, it makes a dipole, an electric dipole. A magnetic dipole transition moment, it's a little harder to conceptualize in our head. Okay, the other metric is brightness that we need to improve, and so we would have to improve mole absorptivity and quantum yield, but also the symmetry factor, right? So that's where we started to think about concentrating our efforts first. How can we improve the symmetry factor? And as I said, we are playing with manipulating dipoles, and for us, it's hard to conceptualize magnetic dipole transition moments, so we tried to play with electric dipole first. So this is the binol ligand that I have shown you that we've worked with, and very crudely, the dipole looks like this, right? And so we thought, can we just change the dipole without changing too much of the electronics of the ligand? Meaning, can we use this isomer that has a slightly different dipole, but has exactly the same number of carbons and oxygen, should be binding the same way. Unfortunately, that binol, we cannot use it because here, these are just hydrogens. And so it's going to, the CC bond is flipping around, so you cannot have an enantiopure ligand. It's going to racemize. So we had to synthetically block that position with extra phenyl groups, but we could get now a ligand that looks very similar to what we wanted. So we coordinated it on the lanthanide, it kind of makes a monster complex. What is important is we get the luminescent complex in the near-infrared that shows CPM. And now we can get the metrics and compare it to what we had before to see if we were on the right track. And I think we were on the right track in one direction, right? The dissymmetry factor is going up compared to our previous one by a little bit. And in the case of erbium, it goes up by quite a bit, actually. But the brightness is suffering a little bit in both cases, so we cannot balance the two at the same time for the moment in that example. So that pushed us to kind of revisit what we've done in the past. And so what we've done in the past is play with the visible emitters. We've used that ligand that is very similar to the binol that you've seen, and we got very high metrics for emission and brightness at the time. And what we've identified in this ligand is one point of weakness. It is that the chirality is imparted by this CC single bond. There is a restricted rotation for sure, but because it's a CC single bond, it can still kind of wiggle around it. So we thought that that was the point of weakness, and so we had to make it so that it doesn't wiggle anymore. And our trick to do this was to use a spiral carbon here that is now completely locked into position because it's not a CC bond and cannot wiggle around. And with this, we could improve both metrics at the same time, both the symmetry factor and brightnesses into like very, very high numbers now. So we thought, well, our near-infrared, I've shown you the first example with the binol, it's exactly the same story, right? It has a CC single bond, it's flexible. Can we put a spiral carbon in it? And then we can improve both metrics at the same time. So of course, this is a nice story to tell as a professor. It's very easy to draw this ligand on the piece of paper. Now you need to go into the lab and make it, and it's a lot of steps. So it's almost an organic total synthesis of the ligand and also the chiral resolution in the end. So I won't talk into too much detail into the synthesis here, but I really want to show you that we can do the synthesis as well, and that's a fun part of the lab, and my students are really good at making those molecules. Okay, so we could make the molecule and also the complex. How does it impact the metrics? So here is the bienol and the vanol, and I'm adding the new one, they're called sphenol. And this one has now the symmetry factors that are a little better for ytterbium, but a lot better for erbium. But again, our brightnesses are low or about the same as our second case. So we still need to work on improving these brightnesses issue. As I said, the brightness is linked to the symmetry factor, right? There is here, so that's why we went there first. But we see that we are having some difficulty deconvoluting the two components. So we thought, okay, let's just think about brightness on its own, and then we'll figure out what's going to happen with the symmetry factor after. So how to go about brightness? Like I said, we're very interested into the erbium work for the telecom applications. And so if you want to play with brightness, you have a lot of things. You can think about how much you absorb here, optimize the energy transfer here to your F star. But for erbium specifically, we were also interested in how to not deactivate the light that comes out of it. So the emissive state of erbium is about 6,500 wave numbers, which if you compare it to a CH bond, you know that's in infrared, this is 3,000 about. So it's very close to the first vibrational overtone of your CH bond. So very often, instead of giving you light, giving back its energy as light, it will give back its energy as CH vibrations, and you won't see anything. So we thought, how can we make this work? Well, you just remove CH bonds. But tell someone that does organic synthesis to remove CH bonds is going to be very hard, right? But we thought about it kind of a crazy way. Instead of having all of this with hydrogens, we wanted to make this all with fluorines. No more CH bonds. And CF bonds vibrate at much lower energy. So to get to a point where you would be in competition to deactivate your F star, you need to be at the 6th vibrational overtone, which is a lot less probable. So let's go to CF bonds. I don't like this because it overlaps, so I'm going to simplify this with like these little dots for CFs. And again, it's very easy to put on ChemDraw and add all of your Fs. In the lab, it's also quite complicated. So it's a fairly long synthesis. You start with octafluoronaphthalene, and you can get to the bienol with chiral resolution as well. So my student was very good at making this synthesis. And then you can coordinate to the metal and make the emitter that has CPL. So how does our metric compare? Well, unfortunately, we didn't predict it, but the symmetry factor is not following the right trend, but the brightness is really, really high. It's the best for erbium, even if it's not chiral. So thanks to these CF bonds, we were right, it really increases the brightness. But here I'm comparing things, and I'm going to put a star here, because maybe they're not quite comparable. So let me illustrate what's going on here. Let's go back to the emission profile. So this is intensity of light versus wavelength, and this is for the bienol complex, the erbium bienol complex. And this one is for the vanol complex, and this one is for the sphenol complex. So they're basically cousins, right? They're all the same, you know they have the same structure. Now you put the F12 bienol, is very different. And this is really very different also in CPL. So this is the CPL of the bienol, and this is the vanol, and then this is the sphenol. So they're kind of the same dots, slightly a little different, right? But your F12 bienol is your ugly duckling, and it's all even turned upside down because that peak is coming down. So what is going on? Unfortunately, we couldn't grow single crystals to kind of get a picture, so we had to do a lot of solution studies to figure out what's going on. But this is what's going on after all of our solution studies. So the normal one, the normal, quote, complex, works like this. There is an erbium in the center, the 3 ligands, and then there is a bridging cation to balance the charge. These are 3 times 2 ligands, so you need 3 cations. And what happens when you have the fluorines, we saw by fluorine NMR and also lithium NMR for the lithium, is that it forces the lithium to interact with the fluorine here to make these lithium fluorine bonds that twist the ligand. And what happens is that now the original one was a lambda chirality at the metal, but now because the ligand needs to twist to bind the fluorine, it changes the chirality of the metal to be delta. And that makes sense with the CPL because the lambda is positive and the delta is now negative. So there are some structural changes that happen because we introduced the fluorine. So now we're still at a challenge, right? We still need to find a system that improves both metrics at the same time in the near infrared, but that's something I think we can achieve in the future. Okay, so in the next 10, 15 minutes, I'm going to switch topics a little bit. I'm going to go down a row in the periodic table and talk to you about actinides. So these would be 5F elements that I have all listed here. There is one challenge to work with this, is that they're all radioactive. So you need the right facility or the right technique to handle those, but that's not too bad for some of those. Okay, so what do we know about luminescence of actinide complexes? There are some reported examples. So you're maybe very familiar with uranium luminescence. So this is uranyl glass. You can buy them like in shops and everything. And if you put under UV light, you get some green fluorescence or green luminescence. It's pretty cool. Other elements, you can actually also get luminescence. So you have americium, curium, and einsteinium that have been reported in the literature. And these all have like the antenna effect with all of those ligands that are the antennas. And so this is a curium example, and then some americium, curium, and einsteinium examples here. Okay, one simplification for the lanthanides, the actinides that I will introduce you to here is that the early actinides from actinium to maybe plutonium behave kind of like transition metals, whereas the later actinides behave more like lanthanides, so americium and moving forwards. So, to no surprise, the luminescence of uranium here, or uranyl specifically, is coming from a ligand to metal charge transfer, something that you see in transition metal, whereas the luminescence in the later actinides are sensitized F to F, what you find in lanthanide chemistry. So now if you want to see circularly polarized luminescence, it's better to have something that resembles the lanthanide, so you need to work with something that is on the late actinide row. So these are getting a little radioactive, so you could think, why are we going to do CPL with actinide? What are you going to do with this? If we put this in a fiber optic, you will make a radioactive fiber optic, so you probably don't want to make a radioactive fiber optic. So let's think about what you can learn from CPL of actinides. So you know that if you want energy, you can use nuclear power plants, and the fuel that you use is mostly uranium. Some in France are using plutonium. And during normal operation, you generate neutrons. And if you generate neutrons with heavy actinides, you actually feed the lower actinides and they beef up and they become new elements. And so you get to generate things like americium to einsteinium. And these have long half-lives, some kind of short, but some that will stay like almost forever in the lifetime of humans, and have much stronger radioactivity than like your uranium or thorium. Okay, so you are going to generate this during normal operation. You know that there have been some incidents with nuclear reactors that can get into a meltdown that would generate more neutrons, so more of these elements that you need to get rid of. And then hopefully this will not happen, but if this blows up, you get even more neutrons and even more of these. So understanding how these elements behave, if you can bind them to remove them, is very important. And so we need to understand their electronic structure. So how do we understand electronic structure using CPL? Let's take a step back and compare a transition metal and a lanthanide here. I think the animation gets weird here, but that's okay. In transition metal, you remember that your free ion is going to be split by crystal field splitting because the orbitals are interacting with your ligand. So this is an octahedral geometry with your T2G and your E. Under a magnetic field, you can see spin-orbit coupling, so you can get a little more information about your electronic structure, but you need to put it under a strong magnetic field. For lanthanides and presumably actinides, it's going to be different. Your free ion is already split by crystal field splitting here, by electrostatic interaction. And then the crystal field splitting is much smaller because your f orbitals are contracted, so they don't interact with the ligand at all. Well, a little bit. So what you see first is spin-orbit coupling splitting, and then your ligands are still tickling a little bit your f orbitals, so you're going to have crystal field splitting. And I will argue that CPL spectroscopy is a very good tool to understand what's going on at the level of crystal field splitting. Let me illustrate why. I'm bringing back the erbium spectrum that you have seen, and let's just look at one enantiomer for simplicity. What you can see here is like there are different transitions, there are different peaks. Some are negative and some are positive. And all of these are coming from crystal field splitting. So this yellow one, for example, that red one, and that green one. And what you can clearly see is that if I look, oh, sorry, this is the wrong step. Okay. So if we compare the yellow and the red here, you can, well, let's compare the red and the green first. By luminescence, it's very obvious that there are two contributions because you have a shoulder here, right? And it's positive and negative by CPL. So in both spectroscopy, it's very clear that you have two transitions. But now if you compare the yellow and the red, by luminescence alone, it's very hard to say that there are two because you can't really see a nice shoulder here. But by CPL, it's very obvious because there is a minus and a positive contribution here. So that's why I think CPL spectroscopy is a little more powerful than luminescence spectroscopy in this case, or you need to use both combined. Okay, so can we do CPL with these actinides? Answer is yes. Someone has reported about 10, 12 years ago a CPL of curium with this monster ligand here. But you see the spectrum is kind of noisy. There's not a lot of information you can get out of this. So we're thinking, can we get more information? So I went to the national lab in the US, in Berkeley, and worked with curium. And we had developed this ligand in the past that was doing circularly polarized luminescence with lanthanide. And it's a very simple ligand that can work in water. So it's very easy for us to translate that technology to work with the actinides. So we transferred that technology to work with curium. This is a pretty radioactive element, so we had to scale down quite a bit. So we're working on the 100 nanomole scale, so very little. But even in the 100 nanomole scale, you can get a very nice, so this is a cuvette under UV, so you can see it's bright orange. And in the CPL and luminescence spectrum, you see that there are lots of features, right? Change of sign here, 2 components there, and then even multiple components here. And with this, by combining luminescence and circularly polarized luminescence, we could map all of the crystal field splitting of curium quantitatively, which has never been done before. So we're very excited to use that for other elements in the future. So we have some other work with the actinides, but here, since I'm running a little out of time, I wanted to talk to you with our efforts to work on the other part of the actinides. So here, these later actinides are very radioactive. You need to go to the national lab to work with them. The ones before, uranium specifically, we can do in our lab. So just for practicality, it was better for us to try to work with this. But this is coming from a ligand to metal charge transfer, so we were thinking maybe it's not possible to get CPL. Can we get CPL out of uranyl? What can we do with this? So this is the picture of an actinide or lanthanide. And for uranyl, it's a ligand to metal charge transfer, but you can also think about it this way. So the orbitals that you have, the ground state is sigma. So it's a bonding between the uranium and oxygen. So it's one of the bonds there. And then the excited state are those delta and phi symmetry f orbitals empty on the uranium itself. And so because these are both ungerade orbitals, we were thinking that in terms of selection rules, that should be pretty similar to the F transitions. So if we can get a system that has sensitization in quotes, maybe we can populate this and then make it emit, and maybe we could get circularly polarized light out of this. So first, we need to see if sensitization is feasible with uranil. There's a report that we found about 10 years ago that reported that if you put benzoates on uranil, you can sensitize uranil luminescence. But benzoate is not chiral, so we want something chiral to get circularly polarized light. And so it took us a little bit to think about the right molecule to put in there, and I think my student had a headache when he came out with the idea, because we use ibuprofen as the chiral ligand here. So here is ibuprofen. So what we do is we went to the pharmacy, we bought ibuprofen, and it comes racemic. And we did the chiral resolution, and then we put it on this to make the uranium complex, and that's probably the least effective headache medicine now, even if it has ibuprofen. But we could make this. Here's the crystal structure. It is kind of cool. It's like hexagonal bipyramidal. And what is important is the luminescence. So here are actually two luminescence spectra. On the dark green on the bottom here, it's when we excite directly at the uranium. So weak absorption, weak emission. And the other one is when we excite at 290, 280. So we're hitting a combination of the benzene ring here and the carboxylate. And the energy is then transferred to the uranyl and then emits. So it's much stronger, and so that was for us proof that we have sensitized emission of that uranyl. So now we can try to get CPL, and that's what we could see. So this is the CPL spectrum. So background is total luminescence, and then the non-zero CPL for the two enantiomers of uranyl. So that was really cool. The metric is pretty good. The symmetry factor is not bad. But what was very intriguing to us is here I'm highlighting the maximum emission of the uranyl. And you can see that the CPL is actually shifted by a few nanometers from that. And it took us a long time to figure out why it was happening. We thought that was an instrument problem, so we did a lot of control experiments and nothing was shifted except this one. Eventually, what we figured out is to try to get to a better resolution of our spectrum. So to get better resolution, you change the bandpass. So here it's actually a fairly large bandpass, so we went to a narrow bandpass. When you narrow the bandpass, you get less light, so we could only observe the most luminescent transition. But now what you can see is that if I'm following this red trace, you get a positive peak and also a negative peak on the same vibration peak here. And so we are resolving two components for all of these uranyl peaks, and that's very obvious thanks to the sign inversion. So what we're thinking is that the picture that I have shown you for the uranyl here is for uranyl without any ligands. So it's kind of the D-infinity uranyl. But here we are in C3 symmetry, and so in C3 symmetry there is no way these two are degenerate. You have to split those. And what we're thinking is now the two components that you see are the two emissive transitions from these two components here. And again, it highlights that this is circularly polarized luminescence combined with luminescence is kind of a very good tool to resolve these electronic states of either curium that I've shown you or americium there, or uranyl here in this case. Okay, so let me finish here. I like to think about CPL as a gemstone. I typically have this as a diamond, but I thought like in Brazil I should have this as an emerald, so I colored this in green. And there are very many facets of CPL that are of interest to us, but the whole community. So I've shown you our work on CPL in the near infrared for quantum information science. I've shown you that we can resolve and help our fundamental understanding of 4F and even 5F elements using CPL. But there are a lot of other things we are interested in. So these are some of the work that we've done or are currently doing, and there is much more coming out of the world. And so when we started this work, we started CPL about 2019, I think. And it's very scary as an assistant professor to go into a very new field. So it was very hard to commit, but now I can say that I have committed fully to circularly polarized luminescence. And I'm very excited to continue working in the field with like friends and colleagues. Lastly, I'd like to thank the people that do the work. The group has shrunk a little bit, but we're rebuilding it. Like I have shown you, they do a lot of synthesis, some total synthesis of ligands. It's really, really cool. I'd like to thank Rebecca Adabler, who was my host doing the radioactive work, some agency for funding, and then just advertising that we can do near-infrared CPL, and we now have a cryostat that can come down to 2.5 K. So there will be some cool variable temperature CPL coming out in the future. So thank you very much for listening to me, and then I'll be very happy to answer questions if you have. Thank you.
Thank you, Mael, for class. Details about CPL. So I will open for questions. Se alguém tiver alguma questão, pode ser.
Great talk, Gail. So this is not my field, so I don't really know too much about it. But so it seems to me, of course, when you have light, there is the wavelength that is important, that determines how much light can be absorbed by the ligand, and then you say there's the circular polarization. So isn't the circular polarization, can that not also have a wavelength? Like how often the plane of the light changes as the light propagates? You didn't talk about that aspect, but I could imagine you could circular,
so the light that we detect has a specific wavelength, and will be circularly polarized light. So I guess the frequency is always matching the emissive wavelength, but then the electric and magnetic components are just shifted by a quarter lambda, the period. Yeah.
I see. Well, it just occurred to me that, the frequency at which the circular polarized light propagates.
Yeah, that will determine your wavelength.
And the wavelength at which it changes its polarization should be matched to the dimensions of your ligand. If you get a good match between the dimensions of your ligand and the wavelength or the frequency at which the polarization rotates, then I'd say your circularly polarized emission will go up in terms of intensity.
Yeah, I think that's interesting. Like
we could talk about it later, but I just
for sure.
Thank you so much. I love seeing different stuff on well-known elements for me. It was really fun. You said already you have cryostat, but the whole time I was thinking everything is based on the Stark sublevels of your crystal field splitting.
Yeah.
So would you expect that when you go to the lower temperatures, you see the Stark splitting much better, and then this has an influence also on one hand side brightness? So for instance, you say the spectrum we can't see that there is actually bump, but in the CPL we can. When you go low temperature, you would start seeing these.
Yeah. So 2 points here. For uranil, actually, the argument we make in the paper is that we see this at room temperature. Because if you cool the uranium sample just by luminescence, you will start to see the two components here. So the attractive part is room temperature. Now, what I want to do with the lanthanides, eventually, if you can find where I have, for example, here, is that, sorry, it's more precise if I point here. These selection rules are well known for the lanthanides, but these, nobody has, do you think? I don't think a lot of people know what the selection rules are between those. And so with the cryostat, you can try to deconvolute all of these kind of from variable one by one and try to figure out maybe what selection rules are between these dark sublevels. So that's what I want to try to achieve with those.
Also, if you change temperature within the brighter regime, or maybe a little bit higher, you should be able to see changes in the ratios, no? Because you're populating higher levels and the sublevels.
Yeah, and so that's why, like, if we go to 2.5K, we should hopefully have only, you know, that one excited state into just these two, for example. So that should be 2 peaks. And then if we increase in temperature, we should see 2 new peaks, and we can determine the sign, and then it may tell us about the why one is more than the other. Like, and Fernando is familiar with this, but within the same transition, some bands are positive, very strong, and some are negative, like very weak. And I don't know why.
The reason for why they are positive and why they are negative?
That's so what we want to figure out. And we're teaming up with computational chemists who are also trying that. But then with the F electrons everywhere, it's very hard computationally. So.
Any more questions? Se tiver questões em português, procure vamos. Also, thank you. Thanks a lot for your brilliant talk. Congrats for the results. My question is about the fluorinated vinyl. Always. And then you saw some distortions caused by a lithium fluorine interaction. Did you saw any systematic change on the G-Lum factor by changing from lithium to cesium, for example? Or even introducing a chiral cation?
We have not played with the chiral cation yet, but let me put the structure back so it's a little easier. So here, when we play with, so we've done lithium to cesium, like all of them, and what happens is, it's not depicted here, but there is a little bit of a cation pi interaction here. So with lithium, there is no cation pi, and it looks like the geometry is then ideal at that point to have slightly higher dissymmetry factor. In sodium, then you have a cation pi interaction, and then more and more as you go to the larger ones, and it starts to distort the octahedron to a geometry that we think is not favorable for having higher dissymmetry factor.
Can I ask another one? Because I have no view, but is the circular polarization of the light having any effect on lifetimes, or can you do measurement of lifetime of circular polarization?
That would be fun, yeah. I don't think anyone can do time resolve. No, that would be cool to know how long it, it would be.
There is any difference.
But wouldn't the measurement be simple? You prove with your techniques that you have polarized light, and then you just put a filter between your sample and a regular lifetime.
The signals are pretty weak in intensity because the difference between the left and the right is very small. So, you would need to have a very good emitter and the right detector. It's just an instrumentation issue, I think. But I think that would give a lot of information.
I think the noise version would be okay.
No, but most of these are like averages of many samples. So,
But it is possible. We just need to start measuring them. It is possible.
I have you say about the brightness, it's part of information what's the presence. But this is always calculated and received for solutions. And about solids. What can we do to compare the brightness?
The brightness, that's an interesting thing. So I think the issue with what is in the literature right now for brightness, to the equation, is that the molar absorptivity, how do you determine this? So now in the literature, it's like the molar absorptivity at where you excite. But some people, I've looked at the data, they don't report that they take the maximum absorptivity and not where they excite, and there is quite a bit of difference. So I think you should get rid of the molar productivity. And maybe just think about efficiency with like quantum yield and the symmetry factor. That way it's like the maximum is 1 or like 2, depending on how you want to calculate it. And yeah, and that way you cannot artificially inflate by having something that has a very high molar productivity for some reason. You're really looking at, if you give 1 photon, it should give you 1 photon out, and it should be 100% circularly polarized. I think it would be more, more scientifically accurate than just like a contest on the number here, and you can play like these. You can play with the numbers to have a higher number. So.
Okay, so let's thank you, Professor Ryle again. Pessoal, agora não tem um coffee breakzinho ali atrás e às 10h50 a gente volta para o seminário da professora Eva, tá bom? Então fiquem por aí. Tem lugar.
We also did this on water, but yeah.
Só se não for tipo.
Eu vou ir
Mas não pode usar.
Yeah, this one we designed so that it would be stable in water, because it's just the purity and the peroxide, so it's soluble and stable, No, not yet. We won't have the detector also for it, but yeah.
In water.
Oh, yeah. Then it is very much you have to bring that in a very gently. And ICAP.
I'm still using this last week. It's good to know this.
Yeah. Do you want to try it like
Yeah, this is
Yeah, I have one also.
No, but it should work.
It should.
I don't have.
Yeah, it's a little different. You have to get the time hammer, but if you
And
there is
go back and forth.
This one is.
yeah. But this one, you
This
can
works
show
for the
one
people
for everyone.
offline, yes. And actually, very often, I think this red dot is easier to see than.
Yeah. I want one.
I want one and one. But here it's easier to control.
Yeah, you can try here, try here, like you can point on that sort of there, and you will see the, like, it's a little more jittery.
Straight line.
But of course, you have a wavelength that is a period between the maximum of the wave vectors. But then, when you look at some of the polarization plane changes as the wide wave properties. Right? Yeah. The question I have, can this is a frequency that can be arbitrarily adjusted. So you could imagine polarizing a wave like this, where the light plane changes very slowly, and then this one where it changes much faster. So this is a separate wavelength that can be assigned to this polarization direction changing. Or is the frequency here determined? Because the wavelength determine how quickly the
This one determines the wavelength of light.
So the wavelength of the light determines how quickly this changes.
It's more like how, so we got that middle one, sorry, is like just, longer wavelength. light circularly polarized message. Here on the right, circularly polarized message. This is a UV circularly
Well,
polarized.
this is just the wavelength of the wave vector. This would be the periodicity or the, you know, the probability of light polarization. I mean, thinking about it, making it
But
possible.
so this one here is a superposition of. So this is actually this plus the one. So this is for if you want electric.
It's the phase shift.
Yeah. So then these wavelengths have to match to give you that.
I see. So you cannot choose arbitrary. Wavelength dictates that.
Yeah.
Oh, I see. Well, but then
Like what you are looking at, I think is like some people try to do is to match the size of the repeating unit of their material
to the wavelength.
to the wavelength so that you can impart this and that will
More for size.
Mhm.
Yeah, more for size. That you, I mean, in the end, you can see exactly the same phenomenon. That's phenomenon. This is for example, a diffraction of visible light.
Yeah, that's right.
That's called polarization. I mean, spell it correctly. Diffraction of the visible light. If you do that, for example, I also do some insects there.
Yeah.
And you see the butterfly. The butterfly, it does have the beat of the butterfly. They don't have it's a refraction rate. So, and those ones are also circular polarized. So the way that they construct this, I mean, if you change the left or right,
It looks like this.
and what's that question I have? Well, I saw that several people are doing that now. If a microcrystalline array of spheres, for example, and you can call that circularly polarized luminescence, or you call light.
Yeah, it's trying to
Should be light. So there are some confusion there. No, because people can together. Then they are getting light, and that light is fractal by these two.
So that's you can have a reflected light and an emitted light, and the emitted light is non-chiral, but the
You can have something like photonic crystal.
Exactly.
This is not a polarized.
Yeah. So
yes,
when I read the picture, there are some strange, like overcorrected material. Yes. They are using, for example, microcellulose.
And molecules like long meters, like nucleotides, where then
That's another dialect. For example, you claim that you can use the CPL for amplification, 1550.
Yeah.
But I don't think that, for example, if you transmit a circular polarized light from here to US, along cable, if over there you still get the circular polarized light.
I don't know how because it's going to bounce off.
Yeah.
So first you cannot just, it needs to be absolute.
Yeah.
and it's like converging out.
Yeah, because all the time that it reflects, it changes the direction.
Yeah.
If it's left and it reflects, it goes right.
Depends on the design of the cladding of the fiber. If that is something like.
Yeah, right, but then just the light.
Can be done.
Write the letter.
Instead of.
Yeah.
If there are any lifetime changes.
Yeah, that will be, we need to figure out.
Yeah.
Polarization, and then that would be very high.
How much, how to say, what is it like the operation, like, each one with operations, like,
As long as
Because we want
but of course, they can use
technology.
This
This is like,
this is bias. Don't have to hurry. Finish your story because it lasts for a long time. You remember.
So this is,
Yeah. First of all, you have to be there. With the, all the infrastructure that you have. And you shouldn't have one, probably not have one nation.
Yeah.
For, more really yeah, that's not that. Yeah, so
By adding and there is expectation between these two monolith vessels.
House circulates. So in yes, you are quickly the wavelength of a tube.
Yeah.
It gives you circularly polarized light.
yeah, I have some, silicon.
So that means yes, by adjusting the phase shift between the two.
Express.
So these are not two lights, this is the electric light. This is the magnetic psychological light.
Because I mean, yes, electromagnetic light always has magnetic and they are comparable to each other. It's just magnetically. What I'm trying to do here is two really polarized, it's just looking at the E vector.
Yeah, no, actually, no, you're right, because when you're going to add the two linear components from that and the two magnetic, and they're both like the degrees. So you just see
It's just between these two different.
Yeah.
But if there's a small phase shift, that would give certain.
You get me? It's the difference between if the phase shift is not 90 degrees, then you have a little.
just going 90 degrees.
What's the difference between elliptically polarized and circular polarized? Is that the same thing?
Yeah.
What I'm trying to say is that for which the polarization changes can be independently adjusted from the phase of these two things. And so it's not necessarily, so you can have two types of the polarized light with the same wave, one which changes quickly and one which changes slowly. And so that's another degree of freedom. There's not just one circular polarized light. Different lightnings have the same wave. Yeah, they're also polarized. Here, in theory, it's much faster. It seems to me it's that period. And you have exactly then one down strong, but if you try to follow strong, and we look at these, we also otherwise interaction. To see the difference.
No, I think that's right. I'll figure out it more. And that's what's good.
With solid state repel. Now, then you can make or you can make. So you can make, let's say, you can polarize with that. 600. I can make a zero. That's what you say. That you have a comparison between your viewer because it's the way.
Yeah, I'm just trying to picture how the negative does polarize somebody. And the only explanation I have is that really somehow causes a different velocity of light
Yes.
versus velocity of light for that.
Yeah.
And it's that velocity of light difference that leads to a small phase shift in the tubes, and that causes the social.
Yeah, that's
Yeah. So then, the size of the incident will have, the size or in fact, increase. Index, that's the velocity of light.
Yeah, so maybe, well, that's what I say. I mean, you want to see it's for example, we have a leak. Well, we have to start to have elements on that. In fact, there's a instead of, I don't know, if I had salvation there, on the leak, that may be. Yeah,
That, of course, electron density.
yeah, then you take the electric,
And the dipole moment.
yeah,
Is key.
yeah. So that's true. You try to see the type of units. In fact, and you say, okay, you went looking up and
Okay. Sometimes,
You are on the left side.
and then, yeah, so we cover the break by
well, sure, they have to be some different here. So.
My question is more like you saying. This is all the questions I hate.
So maybe what's the combination like teaching? Yeah, for that music. Yeah, first year. So yeah, I believe.
Perfect.
So I was looking at your model.
Yeah, that's what I had a discussion with also with Luis, about this, and then we were all like very confused on what financing was actually there, and I think I have to look at the data, but I think what we see is a shift between the excitation and the performance spectrum, which is what we see in the later spectrum when there is an antenna index. So.
Wait, say that again, the difference between the absorption and the excitation?
Yeah. So usually it's just red shift in the excitation.
Oh, not a,
So that was the next line. Maybe it's like an analyze, we analyze this, but maybe there is a different phenomenon.
because that absorption, the excitation.
Yeah, so ours look kind of sharp, like if you go in some of the or you what trying to get better citation. Yeah, exactly. Because even when you're in very careful. I don't think because we see a lot of negative consequences. And so most of them, we just get negative phosphorus and then there's the areas and then for some reason once the area system is like very low huge emissions right? And then our metal thing, we never we never see this. And so we got the triplet of the biggest system. And it made no sense. It's exactly so that's the scenario where we should have variation is a value because the main emissive position you see is no longer
That would be interesting for traffic.
I don't know why, and so what we wrote down is like the big phosphorus. So maybe so that's all of the findings of the complexes. You want one, like the two to be like another parallel, the second one and if you accept that, is it more efficient to track? Yeah, we have like I have a bunch of sketches and then I have more and we'll complete this.
So, right. I think that is a good time. What we learned about the strip of I don't know what Mars is.
Yeah, I don't think it's important, but
It wasn't.
Maybe we get it.
Yeah, that's like change the a little bit by nature, so that's why yeah, that's why people will usually look at linear services or to us in that situation.
So,
Yeah, so then you can use it. Yes, pretty good.
Yeah, you get off of
Yeah, my you don't find that anything like that.
Are you going to pick one?
Yes, for example. Oh my God. Spain?
It's like the seed of astronaut comes back into the station and trying to sabotage the
All the different small library. You can see all this one, all of them when they start, all the two, they close their mouths, not everything. I mean, the beginning, when I you just want very,
Optical excitation, luminescence. So do you often have people from outside Química come here to give seminars? How long have you been?
1 month.
Oh, that's pretty, yeah, we start there.
Yeah.
Oh, 1 year, yeah. Fun. You're not, but this is.
Why is it not, how do you turn it on?
And,
Yeah, you need to change it there. This one right here. No, 3,000.
I don't get anything.
Because from say,
yes.
no, I
But
don't
I really
have.
want to see.
Yeah.
So this is the first year we have bad air quality like this. Did you have that before? Bad air quality?
So you can put there in the show, this is very,
just one thing. I don't know. Kyle said, it's always in the center or the did you send that?
yeah, this one doesn't have the app.
For a long time already, NADE for, right?
Yes. I
15 years, every year, sometimes worse.
Bom, vamos recomeçar, gente, agora. Bom dia, boa tarde, vamos para o segundo seminário. Aí depende. Bom, a gente está sem o registro do cartão, então eu vou passar a mesma folha, gente, aqui, com o nome da professora Eva. Então vocês assinem aqui, coloca o RA e depois a gente vai passar para a pós-graduação para registrar que vocês assistiram o seminário, tá bom? Vamos começar a passar. Hello, I introduce you Professor Eva Hammer. Professor, first of all, thank you for coming. Eva is here for 3 weeks, almost 3 weeks of that. She gave us a wonderful course about lanthanides and materials, lanthanide-based materials. So it's a pleasure to have Eva. So thank you, Eva. And Professor Eva Hammer is an associate professor at University of Ottawa, Canada. She holds a university research chair in materials chemistry in University of Ottawa. She received her PhD in 2008 in a materials science from Saarbrücken University in Germany. She was supervised by Professor Sunhei Matu. during her PhD, she focused on synthesis of lanthanide alcohol sites and their decomposition to lanthanide containing inorganic nanomaterials. This experience was further deepened during her postdoc studies when she worked on lanthanide nanoparticles for near-infrared bioimaging with Professor Kohei Soga in Tokyo, where she spent 3 years.
3 years, almost literally.
So in 2013, she was our Feldor Line Research Postdoctoral Fellowship from the Alexander von Humboldt Foundation. She worked in a group of Professor Fiores Petroni. Professor Fiores Petroni will join us in Belo Horizonte for the Química, and together with François Legarret at the University of Quebec in Montreal, Canada. During this postdoc, Professor Eva worked on the development of nanomaterials based on upconverted nanoparticles. And in the winter of 2016, she came to Ottawa. She moved to Ottawa to design and study novel multifunctional lanthanide-based nanocarriers for biomedical and energy conversion applications at the Department of the Chemistry and Biomolecular Science of the University of Ottawa in Canada. In February 2023, one year and a half ago, Eva joined the editorial board of the Nanoscale Journal and the Nanoscale Advances as associate editor. So thank you for coming, Eva. And we are going to listen a little bit more about lanthanides, that of course is my field of research, and Professor Paulo's field of research also. So thank you for coming, Eva, and for all these 3 weeks of working together. Thank you so much.
Thank you. For the introduction, thanks for being here and to hear about the microwave-assisted synthesis and how we can control structure and also properties of these lanthanide-based materials. But before talking about science, I have to acknowledge all the hard work of my students and also of collaborators, funding agencies, but I think today it's the most important to actually thank Professor Fernando for this amazing time that I have had the opportunity to spend here so far in Campinas. I made love with, I really fell in love with these crazy animals, like the tiny, well, not so tiny, the huge capybaras, the tiny capybaras, and also some crazy birds that we saw at the National Lab. Not to forget some also like very fun time at the University of Sao Paulo. You may recognize some people here as they had also been previously in Campinas. So thank you very much for this opportunity to be here. All right, so many of you work with lanthanides, and we had an amazing talk earlier today about lanthanides. So in principle, most likely, I do not need to convince you anymore why lanthanides are poor. But still, let's have a look. So for instance, lanthanides are very well known for their magnetic properties. So you can, for instance, find gadolinium chelates as like contrast agents for MRI magnetic resonance imaging. Or you find a lot of neodymium in strong magnets that are used in windmills, just to give you an example. This is because of their magnetic properties. On the other hand side, they are very well known for their optical properties. For instance, in laser pointers, this is not a good example to demonstrate this, but also in lighting, just to give an example. We find lanthanides also in security tags. And for instance, if you visit Europe and you take a Euro note, you put it under UV light, what you will see is this beautiful ring in green and in red. And the red actually comes from a europium complex. Someone with a sense of humor, when they designed the Euro notes, decided that there should be europium in there. Or you can have a look at the Chinese money, where you actually find some up-converting materials in there, and we will get a little bit more into what up-conversion is. Those either are established applications of lanthanides, but also there are those that are a little bit the music of the future, but there is great potential. For instance, in the application of biomedicine, as to give you some examples, imaging agents for photodynamic therapy, or also in more precise bioassays. So that's why we really like the lanthanides, to take advantage of their magnetic and also their optical properties. But let's focus first of all on light. And why do we matter which kind of light is used? Professor Gael introduced to us already that near-infrared light is actually of interest, but also when you're thinking a bit more about like potential biological applications, of course, if you break a bone, you go to the hospital, they will put like you on an X-ray in order to get an image that can easily penetrate through the body, no problem at all. However, the issue is that X-ray is not the healthiest radiation to tissue. So if you move to visible light or UV light, in case of this, the problem is light is really convenient to do videos, to recording, to observe something live. However, UV and visible light blocks at the skin. You cannot see what is happening behind my back, and that is good because it would look awkward what I had eaten just for the coffee break. But from a diagnostics point of view, it would be convenient to be able to have light that can penetrate deeper into the tissue. And this is possible if we go to longer wavelengths in the near-infrared spectral region. So that is why there is a big interest in developing probes, molecular and nano, that are able to be excited with near-infrared light, but also emit near-infrared light. All right. So here are the lanthanides. Typically, you see a periodical table like here on the wall. But as someone who's working from lanthanides, this is actually how I think a periodical table should be always plotted, because the lanthanides are the 4F group, so they are here and they are standing out of the periodical table, and they have outstanding optical and magnetic properties. So let's talk about those. Okay. So in my research group, we have several goals, and one of them, and maybe the most important for us, is to develop some new techniques how we can synthesize lanthanide-based nanomaterials in a more reliable, more reproducible, and also faster way, exploring microwave reactions. On the other hand side, of course, it's not just enough to make the material. We also want to know what about their properties, like upconversion, near-infrared emission. Can we make it more efficient? How can we make it more efficient? And last but not least, also to include some multifunctionality. So that means maybe not only optics, but maybe also some MRI or CT capabilities, or to use it as a sensor, for instance, of temperature. And I will show you some examples here today. All right, so just as a reminder for those that are not so familiar with lanthanides and how the optics works there, in case of upconversion, we do something that might sound a little bit crazy, because we generate light that is of high energy out of light that is of low energy. And physics have told you you cannot generate more energy out of less energy. So however, with upconversion, there is no myth involved. This is how it works. So if we look at, for instance, erbium, which is one of the popular lanthanides, as we have heard earlier, you can use near-infrared light, 980 nanometer, and go into an excited state of the erbium. And then, if you look carefully at these many energy levels, there's another one that matches exactly that wavelength, and another one, and another one. So we can use multiple photons to stepwise go to a higher level. That would be like I first jump this little energy on the chair, and then I jump with another little portion of energy on the table. I will not do that, don't worry. But the lanthanides, like erbium, are a little bit lazy in terms of getting excited to these levels. They have a relatively small absorption cross-section. That's why most of the time we combine erbium with another lanthanide, which is ytterbium, that has a perfect resonant energy match here. So instead, or in addition to exciting erbium directly, we excite ytterbium, followed by energy transfer, and then going up into these levels. We can also do similar with other lanthanides, such as thulium, but of course we will not stay forever in this excited state. I would not stay forever on the table. We go down back to the ground state, and when doing so, we are releasing our energy in form of light. In case of erbium, it gives us the very characteristic green as well as red upconversion. Here's an example of a cuvette with nanoparticles dispersed in a solvent. And where the 980 nanometer laser goes through, you see by naked eye this very characteristic green emission. Sodium, on the other hand, is an excellent lanthanide if you're aiming for blue emission, or even UV emission, or also something that scratches at the near-infrared region, the 800 nanometer emission. So we pick our lanthanides depending on which color we want to have. All right, this sounds all wonderful on paper and easy. Unfortunately, there's a problem. And all these transitions and energy transfers that I have just shown you, they are actually FF transitions, and as we have learned before, this is forbidden by the selection rules. So, however, you also have seen photos of the emission, so it really happens. That just means we need to play some tricks in order to overcome these selection rules, at least partially. And one of these tricks is to make molecules, as we have seen, for instance, this morning. Or alternatively, and this is what we are doing in my lab, you can take these lanthanide ions and you dope them into a suitable crystalline host material. And if you make that inorganic crystalline host material small enough, we obtain an up-converting nanoparticle, or UCNP. That is a very common abbreviation. All right, so that is what we will talk about today. Now the question is, what kind of inorganic crystalline host material can we pick? And if you look into the literature, the most popular ones are actually of the general formula alkali metal, rare earth, fluoride. To give some examples, sodium gadolinium fluoride, sodium yttrium fluoride, lithium yttrium fluoride are very popular for several reasons. What is interesting here is that if you look, for instance, at sodium gadolinium fluoride, you can see I wrote a beta and an alpha here. And that means that this material can crystallize in two different polymorphs, either a hexagonal lattice or a cubic lattice. Now, when we are doping our lanthanide ions into these lattices, they occupy slightly different positions in the lattice. And this has an effect on how efficient our FF transitions can become. So consequently, from an optics point of view, typically we want to have the hexagonal face of our material because this is the more efficient host material for upconversion emission. Nonetheless, do not ignore the cubic phase because, for instance, we have shown that if you compare sodium gadolinium fluoride in the cubic and in the hexagonal phase, and you look at the MRI magnetic properties as a contrast agent, the cubic one outperforms the hexagonal. So, depends a little bit on what you want to get. All right, so in other words, when we make our inorganic materials and we dope them with lanthanides, it's a little bit like baking cookies. Imagine you like your cookies with chocolate, that gives you one flavor, or with nuts, or with marshmallows, this gives you other flavors, or you want to mix them. This is how you give it a specific flavor. This is how we pick our lanthanide ions. But you want to make sure that they are properly distributed, no agglomerations, no clustering, no intermixing. On the other hand side, you also know that a cookie is only really tasty if the cookie dough is good. So we cannot ignore what happens with our inorganic host material. So it's really important to also be able to tune that hexagonal versus cubic sodium gadolinium or sodium yttrium fluoride material. And also the size plays a role. All right. So one of the first things in my research group when we started was actually looking into literature and to understand how can we make these materials using the microwave, but in a controlled crystallographic phase. Good. Now, then also over the last years, we looked into how can we control size and how can we make core shell architectures. And last but not least, I will also touch very briefly on what about alternative materials. But let's get started with the controlled synthesis of the different crystallographic phases. So when we started, we looked into the literature and there was a paper that uses lanthanide trifluoroacetate together with sodium trifluoroacetate as precursors, which is also the very common chemical starting point when using or when performing a traditional thermal decomposition to obtain these materials. So in a traditional way, you would mix these precursors in high boiling point solvents and you heat this up to 300 degrees or more for an hour or longer, depending a little bit on your setup, to get the materials. Now here you can already see what is the advantage of a microwave. It's 10 minutes compared to like an hour scale. So the microwave allows you to obtain something that is much more rapid. And another advantage is a microwave reactor is very rigid. You have your vessel that goes into the cavity and it sits there always in the same way, and the heating is always the same. If you use the 3-neck flask in the heating vessel, it can be like this, like that. One thermocouple is here, another one might be a little bit different, and all this can mess up your parameters. So the thermal decomposition is very well known, it works. But I think personally there's a lot of differences from student to student, from batch to batch, from lab to lab. So can we get rid of that by using a microwave? And people had shown we can use the microwave to get very nice upconverting nanoparticles by using this reaction scheme here. But as you see, it's written alpha. So remember, they reported the cubic phase that we do not want. We wanted to have that hexagonal phase. So that was the starting point of our research. And we were really curious, what do we need to do to get this hexagonal phase? So my first, at the time, master student, now she is ready to defend her PhD thesis next week. She figured out that we have to increase that ratio between gadolinium and sodium ions, putting in sodium ions in excess to push to the hexagonal phase. However, if you look carefully, you also see that I write hexagonal sodium gadolinium fluoride. Nothing about any emitting lanthanide. Because as soon as we added our ytterbium and erbium, it was back into the cubic phase. This did not work. So very disappointing. Nonetheless, this study allowed us to do the MRI dependence on the crystalline phase. And my students and postdocs didn't give up, and they kept further investigating the reaction parameters. So what we found is that we need to provide even more excess of the sodium source and further fine-tune the overall precursor concentration in our reaction vessel. And then we were really able to obtain our hexagonal phase upconverting nanomaterials. How do they look like? So here you can see some TEM images, and indeed, if we are using these traditional lanthanide trifluoroacetates, the particles are very monodispersed. They are not agglomerated because they have the oleate capping on the surface. It's very reproducible between 5 and 6 nanometer in size. So they are tiny. We can make them even smaller. So size control is possible by changing a little bit the precursor chemistry, for instance, to lanthanide oleates or to commercially available lanthanide acetates. Then they become as small as just like 3 nanometer in size. So tiny, does this mean that they are super dim? Yes, it does mean. And this means we need to play a trick. We have to provide them with a protective shell around, as shown in this comic here. So we have like the doped nanoparticles inside, and then outside we are adding another sodium gadolinium fluoride shell that does not contain any emitting lanthanide ions. And then, even though they are still very small, still smaller than 15 nanometer, they give us a very nice and bright emission. So this is just a hand-hold 980 nanometer laser pointer, and you can see how we have a nice green emission when erbium and sodium is doped into the hexagonal phase of sodium gadolinium fluoride. Or alternatively, we get more of the red emission of erbium if it is in the cubic phase. What is this core shell concept? So just to make sure everyone is on the same side, and if you have not come across core shell nanoparticles, let me explain a little bit more. So why do we need this? On the one hand side, yes, to boost luminescence efficiency. And this is typically the very simple, just a core, doped and an undoped shell. But we can also make multi-shell architectures, where ideally you can have, for instance, different lanthanides in different regions of your nanoparticle in order to optimize properties. Okay, this is a little bit like an onion, like onion rings that give you the different regions of the nanoparticle. But if you're more like someone with a sweet tooth, you could also imagine this like maybe a chocolate, where you have, as in these Italian ones, you have a nut and you have chocolate, and all of this is then surrounded by another shell. Or you could also imagine you have a praline that is very soft and it's delicious, but it's easily squished and ruined. So the pâtissier would add like another hard shell around it to protect it. So similarly, we don't make chocolates, but we make our lanthanide core shell architectures. Okay. So if we come back more to our energy levels of the lanthanides, and I do not expect from you to be able to see all the details here. This is just for illustration. So we have different lanthanides with many different energy levels, and we do our excitation. For instance, this up conversion. So we are in excited level, and imagine there are several lanthionide ions next to each other. So that means there can be some energy migration from lanthionide to lanthionide, and at some point, hopefully, it will go down radiatively to the ground state, and we have our emission. That's the ideal scenario. However, if you have a nanoparticle, what can happen without any shell, there's energy migration until we hit the surface of our nanoparticle. And there we have defects in the lattice, we have solvents with, for instance, OH or CH vibrational modes, and all this can lead to a loss of photoluminescence. That's why we add a shell to prevent these effects that ruin our luminescence. Also, what can happen if you have actually lanthanides that are too close to each other, and one would go down only halfway, this energy can be used to bring up a neighbor also just halfway. So they cancel each other out. This is called a gross relaxation process. So sometimes this can help you to tune color, but sometimes it can also ruin your luminescence. So these are some basic mechanisms why we are interested in controlling the interaction between the lanthanides by putting them into different regions within our core multi-shell nanoparticle. Good. So if we go back into the literature, thermal decomposition, the growth of a shell is no problem at all. But remember, we wanted to have that possible with the microwave because it is more reproducible and faster. And the question is, how can we control now the shell signal of our system? So Nan was preparing a set of nanoparticles. You see here like 3 different batches, 3 times very similar sizes of our nanoparticles. And then she grew a shell. This is actually a sodium gadolinium fluoride doped with erbium and ytterbium. And then she grew an undoped sodium gadolinium fluoride on top of this, but with thicker and thicker shells. So how is this possible? What we do is we first synthesize our core, we wash them, then they go back into the microwave reactor, and then we add different amounts of shell precursor. So this is the ratio that we have to tune. And if we are adding fewer nanoparticles, this is what given here is the milligram, to the same amount of molecular precursor for the shell, we grow thicker and thicker shells. Unfortunately, we haven't completely figured out and controlled that yet, because if we go like too far in the way, what we observe is the formation of these flowers, where you start the nucleation of additional nanoparticles on the surface of the core ones. And while the flowers look beautiful, this is usually not what you want because the shell is not efficiently protecting anymore your lanthionide ions. All right, so we cannot only grow a first shell, but Nan also developed a protocol to add like a second shell. And in this case, it's a sodium dysprosium fluoride that is then like at the outer shell. So we have in total a core, shell, nanoparticle. Why do we do that? Okay, so here is the idea. We have in the core, we have erbium, and erbium is used for the photoluminescence, potentially imaging, or photodynamic therapy, ideas like this. But we also wanted to add a magnetic lanthionide ion, like dysprosium, that gives us a contrast for magnetic resonance imaging. And dysprosium is of particular interest because dysprosium allows us to go for magnetic resonance imaging at a high magnetic field, like 7 Tesla. And this is something medical doctors are interested in because it gives you a better resolution. So the question was, can we combine optics with magnetism, erbium and dysprosium? The problem is, we can make a sodium dysprosium fluoride and dope erbium into it. But then look at the up conversion spectrum. This is so terribly noisy. Actually, the luminescence is really like lost. This is not what we want. And based on literature, more like on bulk classes, what was reported before is that now we have a lot of dysprosium in our host material and just a few erbiums here and there. There is this problem of these levels here and these levels over there for dysprosium. They are good matches, so there might be energy transfer that depopulates our emitting erbium level. So the question is, on the one hand side, how can we prevent this? On the other hand side, is the energy transfer happening here at the high level, or is it actually happening here at the lower level? We got inspired by work in the literature, including some nanoparticles that were synthesized by the group of Professor Fernando, where the different lanthanides had been separated into different regions of the nanoparticles. And in particular, we made our erbium in the core. We had this undoped barrier first shell, and then outside we put the dysprosium because we also wanted it to be able to interact with water for the MRI. All right. So to show you step by step how we construct these nanoparticles and what is happening, the core-only nanoparticles are pretty small. And because they are so small and there is like no protection from water, the luminescence is terrible. But look at this. Now, if we are just throwing this first shell that is undoped, for instance, in this case, it was the 4 nanometer thick sodium gadolinium fluoride shell, this boosts the emission significantly. We have the green and the red upconversion emission. And I'm not sure whether it's actually visible, but in the baseline, there is still a little green line that was the core only. And you can see how now the blue with the shell boosts the emission significantly. Then the question was what happens if we are now adding our sodium dysprosium? Will the dysprosium quench the erbium emission, or can we actually keep up with this level of emission? Now, to our surprise, we did not only keep up with the emission, it became even higher. So now we had a nanoparticle where we separated erbium and dysprosium far enough from each other, so there was no more quenching going on, or at least we believe that, and we can have some nice luminescence. To understand a little bit better, we also thought like, well, do we need that 4 nanometer intermediate shell to separate erbium and dysprosium? Or what happens if we just make it a little bit closer to each other? So this is an example where the intermediate shell is only 3 nanometer. And what you can see in comparison, the core shell, nanoparticle in blue, without dysprosium, and then in red is after the addition of dysprosium. In this case, the presence of dysprosium leads to the loss of luminescence. Though these 3 nanometer are not enough, we need at least 4 nanometer of a distance. Of course, we also looked into even further, and like a 6 nanometer shell, and overall it's the same trend as for 4 nanometer, just you boost your emission overall. So, does this really mean that there is no more dysprosium-induced quenching? In order to answer that question, and also the mechanism, is it the quenching through the lower level or through the higher level? What we did was time result measurements. So we looked at the lifetime. And in particular, we looked at the tail of the ytterbium emission, not of the erbium emission, because we wanted to see what is happening here with this intermediate state. Is this maybe depopulated through the dysprosium? And indeed, this is happening as the shortening of the lifetime can show us. The blue values is for the core only nanoparticle. Then in green, or like cyan, we are adding the undoped shell. Consequently, the luminescence lifetime goes up. This is because of protection. But as soon as you are adding your dysprosium, and the dysprosium and the erbium is not separated enough, you see how the lifetime is getting shorter again. So dysprosium is really depopulating this intermediate level here and triggering then the inefficient upconversion process. On the other hand side, if we go to the nanoparticle where we have like a thicker shell in between, we would expect that the lifetime stays the same. It shouldn't change when adding the dysprosium. However, as you can see here, we have our core that would be the same value as this one here, tiny nanoparticles. By adding a thick shell, it really makes the lifetime longer. It protects very well from quenching. But to our surprise, upon the addition of dysprosium, there were still quenching effects. Even so, overall luminescence intensity goes up. So we were not able to completely prevent the quenching, even though emission stayed efficient. And it was the same trend even for the 6 nanometer intermediate shell. Okay, so we understood a little bit better what dysprosium is doing to erbium, and we not only restored the emission, we made it even brighter. But what about the MRI capabilities? In order to test the MRI capabilities, we took our core with the 4 nanometer intermediate shell optimized through the optical studies, and outside is our sodium dysprosium fluoride shell. And here again, we used what we have learned how to control the thickness of these shells, and we grow sodium dysprosium fluoride shells of different thicknesses, so adding more and more dysprosium. And as you're doing so and looking at the MRI performance, we see a higher performance where we are adding more dysprosium in our nanoparticle. This is shown if you look, for instance, at these graphs here. What you're seeing are phantom images. So the more of our nanoparticles we are adding for each of the 3 samples, the darker the image gets. And this is expected because dysprosium is a darkening contrast agent. So this image shows us, yes, it works. And from these graphs here, we have the relaxivity plotted as the dysprosium concentration. What you're interested in this plot is the steepness of the slope. The steeper it is, the better is the performance of your material. So again, by tuning the thickness of the dysprosium containing layer, we obtained better and better values. And here is just like the rough value given that we have been obtaining. And when we compare this to the literature, we were actually very happy to see that it is outperforming what had been previously reported. Now, lanthanides are not only good for magnetism and optics, they are also heavy metals. And it means you can use them for X-ray attenuation, means computed tomography. So another imaging modality that could be added. And just as a proof of concept, we again now looked in with our 3 samples with more and more dysprosium, how they give us a brighter and brighter image because they are better and better in attenuating the X-rays. And here again, we want to look at the slope of these curves for our nanoparticles, and in particular in comparison to the clinical agent, that is iohexol, and you can see that they are all outperforming the performance of the iohexol. So giving us some potential multimodal imaging agent. Of course, toxicity in nanobio is a whole different question. Don't nail me down on this at this moment here. All right. But this is the first example to show you how controlling the architecture of the nanoparticles, we can understand optical properties, and we can also optimize, for instance, magnetic and CT performance. All right. So this was some introduction to the synthesis and some potential use of bioimaging. Let's move to something different, which is actually sensing. All right, so I believe everyone is familiar with temperature sensing because in particular during COVID, measuring our temperature was very important to check do we have a fever or not. Also, if you're a chemist, you very often want to know what is the temperature of your reaction. That is crucial to see whether it works or not. Also, temperature sensing is very important for a lot of different industries, from automotive to petrol to health, you name it. Now, not all the time we can just stick in a macroscopic thermometer. This will not work. For instance, what do you do if you have a tiny microfluidic device and you want to know what is the actual temperature locally? Where is my reaction happening? Is it exothermic or endothermic? Or imagine you have a biological sample where there are some tumor cells and some healthy cells, and you want to know what is what. Is there any tumor or not? And tumor cells have a higher metabolism, consequently their temperature is higher. But again, we can't stick in there just like a macroscopic thermometer. However, you guess already, we go to nanothermometry. So how does this work? Many lanthanides, they have spectral features, for instance, the ratio between their peaks, their lifetime, the risk of their peaks that can be influenced by the temperature around them. And this can be used to sense temperature. The most popular lanthanide that is used for this is actually erbium. And I show you I decided not to go into detail with this because, well, erbium shows us upconversion. And we wanted to move to the near-infrared spectral region, because if you want to do bio applications, it's not only important to be able to penetrate in, you also need to come out with your light. So we also need to have, indeed, a lanthanide ion that is emitting in the near-infrared spectral region. If you look into the literature, you find several examples, from neodymium, holmium, erbium, thulium, very popular. But there is, as we said, the forgotten lanthanide. Of course, if you go to laser physics and classes, you will see a lot of praseodymium. But at the nanoscale, praseodymium is not very well studied. So we were very curious to see what is happening to praseodymium. And we were also inspired by the literature because indeed, praseodymium is giving us a nice emission in the near-infrared spectral region. So it's actually that green curve here, where we have a maximum peak at 1,300 nanometer, matching very well one of these biological near-infrared transparency windows. on the other hand side, the visible emission of praseodymium has been reported to be temperature dependent. And this is happening because if you look carefully, these two energy levels are very close to each other. Now, if you change temperature, you provide energy. What happens? Instead of populating this level, you populate the higher one. So instead of having emission from this wavelength, you will more see emission of that wavelength. So the ratios are changing. All right, so let's take our praseodymium and see what happens in the near-infrared spectral region. And my master student, Abby, she constructed these 4 different types of core multi-shell nanoparticles, where we put actually in the inside, in the first core, either praseodymium or holmium. And then in the second shell, it was the flip, so either holmium, praseodymium undoped, or praseodymium, holmium undoped. Why holmium? Because holmium is another near-infrared emitter that emits at 1,200 nanometers. So now we have 2 different near-infrared emission bands that we can use to play around. So in the interest of time, I will not discuss all of the different features of these 4 architectures, but I will show you only what is happening to the best performer of these materials. All right. So, as already mentioned, thanks to the presence of holmium and praseodymium, we see this emission here, and we see the second emission band there. And what is happening under near-infrared excitation, we are having a resonant energy transfer over to our praseodymium emission. It goes down to this level to give us 1,300 nanometer emission. But if we look at actually the difference between ytterbium and holmium, there's a little bit of a gap. And that little gap, we can take that to our advantage. Because now if we are adding temperature, we can foster that transition from the excited ytterbium to this excited level of holmium. This is a so-called phonon-assisted energy transfer. Phonons is temperature. So what we expect is that if we are now increasing the temperature of our system, this emission band here of holmium should go up in comparison to our praseodymium emission. And we can use it as a nanothermometer. And indeed, this is happening. So what you can see here from our data as a function of temperature between 15 and almost like 50, 60 degrees Celsius, that emission band really goes up. While this is normalized, so this one stays pretty much constant. What we do not just take now the emission intensity. We could say, well, let's look at the intensity and we know whether it's hot or it's cold. This is not really a smart approach, because you would not know whether you have a low temperature, a low signal because of the temperature, or do you have a low signal because there are fewer nanoparticles. So you need to get rid of, for instance, concentration effects. To do that, I introduced the luminescence intensity ratio that is a well-known figure of merit in nanothermometry. So you define your bands and you integrate over them. And in this case here, we integrated then the holmium and the praseodymium emission and plot this ratio as a function of temperature. And as you see, there's a strong dependence. So this is good. This shows us that indeed we have a nanothermometer. But it does not tell us yet, is it a good one compared to the literature? In order to see whether it's really a good nanothermometer, we have to introduce and consider another figure of merit. And this is the so-called relative thermal sensitivity, where we use the slope or the deviation of in each point of this fitted graph here and divide it by the respective luminescence intensity ratio. And if we do this for our nanothermometer data, in this case here, we obtain values that are well above 2% per degree. And this is good, because the field agrees that typically what is higher than 1% is actually a good nanothermometer. Now, in near-infrared, typically you have even lower thermal sensitivity. So we were very happy to see this value here. But there's something I did not mention yet. So, of course, if we compare our performance with others, some of them are better, some of them are worse, but we need to be honest in what condition we measure. And what do I mean by that? That is, do we measure in the cryogenic regime? Do we measure in the biologically interesting regime? Do we go to high temperature? But it also means, do we have a dry powder, which is always much easier to measure? Or do we have something in hexane or in toluene? Or do we have actually something in water, which is the most relevant for real-life applications? So, to be honest, at that point where we have this great performance, we were cheating because we used toluene and not water. But still, okay, let's move our nanoparticles to water. And we do this by using a very simple, not the best choice, but for this study it was not the motivation to make the best water dispersible probe. It was to bring the particles into water and to test nanothermometry. We simply coated them by citrate. And this allows you to make your nanoparticles swim in water. We did this, and we went back to our spectrometer to measure the temperature-dependent spectrum. Now, we get still our nice praseodymium emission band, but what happens here? The holmium is completely gone. So, did we lose and we can forget about our nanothermometry because we cannot make anymore our luminescence intensity ratio? Well, of course, the answer is no, otherwise I wouldn't show it here. Because if you look very carefully at that praseodymium peak, so forget about holmium, we only look at the praseodymium peak. If you look very carefully, you see that on one side here, as a function of temperature, the intensity goes up. Then we reach an isothermal point, and then as a function of temperature, the intensity is going down. So why is this? This is because this is not just like one band, it is actually the envelope of several emission bands that stem from the sublevels of our lanthanides, as we have already heard earlier this morning. So praseodymium as well has this subsplitting into peaks, and what you can do now is a so-called single band nanothermometry. Single band because we use only one FF constituent, not like holmium and praseodymium, but only one. All right. So the idea is not completely new, but it is something that has just started to gain momentum. There are two examples at the time in the literature, one based on erbium and one based on neodymium. And as you can see, the thermal sensitivities are relatively low. Nonetheless, there's a big advantage of single band nanothermometry. And this is because now you use two different wavelengths that are very close to each other. If you think about light-matter interaction, light is going through your body, ideally, at some point. And there is water, there is proteins, there's blood, there's biological matter. And each wavelength might interact in a different way, which can have an effect on your calibration curve for nanothermometry. However, if the wavelengths are close to each other, if there's less of an effect on your overall and from the overall environment, and it can make a nanothermometer more reliable. All right, so we quantified the performance of our material, and there we can see again how we have our isothermal point, and we can now define one area is on this side of the isothermal point, the other one is on this side, and again we have a nice temperature dependence. And also, the SR value was actually pretty good compared to existing ones within the literature. So, just to look a little bit more into the mechanism, what is happening there, because I told you it's based on the Stark levels. But you could say, well, you just showed us a very non-resolved spectrum, and how would you believe me? So we also looked at low temperature spectra of our nanomaterials. Of course, this was then in solid state. And now you can nicely see how there is indeed the subsplitting of the luminescence. And if we go to low temperature, we get like emissions that are coming more from these lower lying Stark levels in blue. It is this one here. However, if we go to higher temperatures, you see how the spectral shape is changing, and we are bringing up this emission intensity here that stems from the higher lying Stark level. So we have the change in the ratio that allows us to perform the nanothermometry. All right, good. Now, this was another example to show how we can control the performance by having separate lanthanide ions in different regions. But a referee asked a very good question. Do you actually need to separate holmium and praseodymium in core and shell? Why not just make your life easy in synthesis and put them all together in the core? So we tested this, and interestingly what we see is that if we put them all together in the core, we cannot do anymore that single band nanothermometry. It does not work anymore with our praseodymium peak to see these nice the splitting into the Stark levels and to see that temperature dependence. Most likely because there's too much energy transfer between praseodymium and holmium and ytterbium, and this is ruining the emission. So again, core shell architecture design is really important to optimize your product. Okay, just a few words in mind with like biomedical applications. And I said in this example, we just did very simple citrate coating, but maybe we as a community, we need to think about better surface functionalization that provides stability in biological media, that provide non-toxicity, and so on. So we look a little bit into this, and one example is, for instance, biopolymers that can be derived from corn. And this is this little guy who's eating the corn here. That's not actually a picture that I took, but it belongs to this company with which we had a collaboration. What they are doing, they are preparing phytoglycogen nanoparticles, and phytoglycogen comes from corn starch. So it's FDA approved, it is allowed for human consumption, you find it in medication, in cosmetics, as a stabilizer, it's very well approved. So our idea was, can we combine this phytoglycogen nanoparticles with lanthanide nanoparticles to make them potentially interesting for biomedical applications? And a former student of the Sigoli group, Emily, she developed a very easy protocol where it's a simple mix and match between these phytoglycogen cornstarch-based nanoparticles. They are about 80 nanometer, and tiny lanthanide doped nanoparticles. We thought maybe there is like a decoration of the 80 nanometer biopolymer with small nanoparticles, but this is not happening. What is happening is we are forming like a submicron vehicle. So this scheme shows you outside, we have the phytoglycogen nanoparticles, and inside we have a lot of small upconverting nanoparticles. And of course, we can choose different colors emission for our upconverting nanoparticles by picking erbium or thulium, for instance. So here you can see a TEM image where you have the very low contrast, that is the organic, the biopolymer shell. And inside we have the assembly of many upconverting nanoparticles. They are so big that we can observe them in our light microscope, and we can use the 980 nanometer laser that is coupled to it and excite one of these beads. And you see the very bright green, yellow emission that comes from erbium. But as I said, we could also choose thulium for blue emitting ones, or combine thulium and erbium to give us something that is more like cyan. And why is that of interest? Because you can also then combine, for instance, a lanthanide nanoparticle with another dye, material, maybe a photosensitizer, a drug, that together they will form further resonance energy transfer flows. So imagine this is your vehicle, and inside is the lanthanide doped nanoparticle, but we co-load something that would act as a drug to trigger photodynamic therapy. We used a model ion, rose bengal, and we co-localized it within our vehicle. Why rose bengal? Because in green here, you see your spectrum, the emission green of erbium. And in pink, you see the absorbance band of rose bengal, and it's a very good overlap. So that means when the nanoparticles and the rose bengal are close to each other, the lanthanide nanoparticles give their energy to the rose bengal, and under near-infrared light, we can trigger also the emission of rose bengal. So this is an example of a thread pair that we can build in these submicron vehicles. To confirm that we really have it co-localized, we also looked at hyperspectral imaging. This is a cluster of these vehicles, and we see the green and red emission that comes exactly from the same spot where we also have the emission of the photosensitizer. All right, but this still does not tell us anything about nano-bio interaction, and also honestly, they were a little bit too large. So we thought about other alternative biopolymers, and we got interested into gamma rubic. Why gamma rubic? Because again, it is FDA approved, you find it in a lot of daily life applications, and it has been shown with metallic nanoparticles to be great for dispersion stability. So we picked this one to see how it would make our nanoparticles biocompatible, or maybe not, in comparison to other approaches. Therefore, we used a very simple core shell architecture nanoparticle with erbium and ytterbium inside. And as you can see from our TM images, when adding the gamma rubic, they become dispersible in water, but it does not affect the morphology of the particles. We also choose two different control samples. One of them, LF, means ligand-free, so there is nothing on the surface. And the third one is PAA, that is polyacrylic acid, which is a very popular ligand to make these nanoparticles water dispersible. Interestingly, already just looking at the dispersion stability as a function of time, after like several months in water, with PAA, you see terrible agglomerations. The same for the ligand-free nanoparticles, while those that are coated with gamma-arabic are way more stable in dispersion over long term. But more interestingly are the results in terms of toxicity. So if you look at these green bars, the green bars are always the ones for the gamma-arabic coated nanoparticles, and they constantly outperform the ligand-free as well as PAA-coated nanoparticles. And it came a little bit to a surprise because PAA-coated nanoparticles are very often reported in the literature as non-toxic. So our results show the complete opposite. So this is an example that I believe the nanotoxicity community needs to do more because we are far away from understanding what's going on. But not only the cell studies are of interest, we also wanted to know what is happening, for instance, in vivo if we expose these different types of nanoparticles to zebrafish. And zebrafish are very interesting because they have a surprisingly close gene characteristic to humans and can be used as models to study human diseases, for instance. So typically what we did in this case, after having like just the fertilization of the eggs, we start having these larvae, and then we're exposed to nanoparticles to then see what is happening in terms of survival, in terms of hatching, and also in terms of their behavior and deformity of the zebrafish larvae in the egg. So very briefly, what we can see is that for gamma-arabic, we have very good results, independent of concentrations of nanoparticles added to the zebrafish. There's no effect on them, in contrast to ligand-free, and this is another example, not only for the cells, but also on the zebrafish. The PAA-coated particles really have a terrible influence on the survival rate. All right, so maybe we should go away from these easy PAA surface modifications. But I also wanted to come back to the hyperspectral imaging that we have already seen with the example of the vehicles. Now, we can also use this in order to map whether nanoparticles are inside of the cells or whether nanoparticles are uptaken by the zebrafish. And this works like point by point, pixel by pixel. You go over your region of interest, and then each point will contain a spectral information. So we can make sure that this is really our erbium emission and not whatever background. And also what you can see, if you take this zebrafish example and you shine UV light on it instead of near-infrared light to trigger up conversion, you see how much background emission you're getting from the UV light. So this gives you, with the near-infrared, the up conversion emission on the near-infrared excitation gives you much better resolution than when you have all that blurry blue emission on the UV excitation. All right, good. So we also looked into the biodistribution of the nanoparticles. Indeed, the particles coated with PAA, all fish were dead. Couldn't even do biodistribution anymore. But for the ligand-free and for the ones with gamma-arabic, we saw some interesting differences, that in one case, the nanoparticles are mainly found in the mouth and in the head area, while for the other case, this is the ligand-free, we also observe them in the tail. So now we want to go into deeper studies looking gene expression to better understand what is happening there. All right, but gamma-arabic, in my opinion, is a promising surface functionalization molecule, because their application is very simple. It's a very easy process to surface modify the nanoparticles. It's FDA approved, and it seems to be very promising in terms of biocompatibility. Now, I should also mention that, to be honest, uptake is low. So the next step would be, can we use these sugar molecules to further functionalize? Good. All right. So I should come more towards the end, and very briefly, I wanted to talk about, we went in this direction here, where we made our particles larger and larger core-shell sharp. What about the very small ones? Remember what I showed you here, these tiny ones? And even if they are, imagine they are cubic and tiny, and they just have an erbium, that is definitely what you would not want for luminescence. But there's something interesting here in terms of magnetism. So this is a collaboration with my colleague Murali Murubiesu, who is an expert in single molecular magnets. Let's not go into detail of those because I'm not an expert. I want to focus on how we need to design the materials. But single molecular magnetism is of interest, for instance, for applications in quantum computing or other related to this. The key point is Usually you have to make these at very low temperature in order to see the effect. And we have shown, for instance, examples also in collaboration with Professor Fernando that we can use molecules where you can sense at the same time temperature and have SMN behavior. But what about all this at a nanoparticle level? Can we have a nanoparticle that would act like a single molecular magnet or a single, maybe molecular is not the right word anymore. So what we did, we made these tiny nanoparticles, 3 nanometer in size, and we wanted to see, can we induce this characteristic of slow relaxation of the magnetization at a materials level, nanoparticle. To do so, we decided to dope with erbium and to put in fewer and fewer erbium ions per nanoparticle. So we reduced the dopant concentration from having something like 10 erbiums per ion per nanoparticle to 8 and less until we ended up with just 1 erbium ion per nanoparticle. And when doing this, then indeed, as these data show you, we can see the dependence of the frequency dependence that we are having here of our signal for the typical magnetic properties. But we see this only if we separate the lanthanide ions very far from each other. So only if we have just 1 erbium ion in 1 nanoparticle. Then we are indeed able to have like the slow magnetic relaxation in our nanoparticle where we have only this 1 erbium ion. So this is, last but not least, also one of the examples where tuning the size and controlling the ions, we can induce new properties into our materials. All right, good. We talked about this, and as an outlook, and also to be honest and show you a little bit of the remaining challenges of microwave-assisted synthesis, yes, we can play with the whole series of lanthanides and obtain for all of them, like sodium praseodymium fluoride, sodium terbium fluoride, you name them. In the cubic phase, no problem at all. They all look beautiful in the synthesis. However, what about hexagonal? I told you we struggled a lot with the gadolinium cubic versus hexagonal, and we found a way to control it. But our choices are limited at the moment. As you can see from this example here, we are good for the early lanthanides, but as we push, for instance, for sodium yttrium fluoride, it doesn't work anymore. We cannot get hexagonal yet. So this is still work in progress. And another problem that we are having is, for instance, lithium yttrium fluoride. We can make these very nice microparticles, but nano, not yet. So this is also still something that we need to find out how to make it in the microwave. On the other hand side, the microwave protocol has been shown to be flexible for materials such as sodium manganese fluoride, where we can also control the morphology by controlling the ion ratio in the reaction mixture. And what we are currently exploring is actually the synthesis of gadolinium oxysulfides and other lanthanide oxysulfides, where we see again that the ion ratio is really crucial because it allows us to either have like these super thin triangle-shaped nanostructures, or we form something that is more like a spherical agglomeration. And there I hope also to get into some collaboration with the Universidad Sao Paulo and to see maybe not only optical properties, but also scintillating properties of these materials. All right, so take-home message. I hope I could convince you that the microwave approach can give us nice particles in a reproducible way. We can control the crystalline phase to some extent. We can also control the size at the smaller size range. It's difficult to make them 20 or 30 nanometer. We figured out a lot about how to do the shelling. Even so, of course, we love drawing these schemes where you have really hard boundaries between a core and the shell and the shell. Probably not so true. Intermixing is also an open question that has to be addressed. If you're interested in the material synthesis of these materials, I would like to recommend you this chapter in the Handbook of the Physics and Chemistry of the Rare Earths, where we discuss also like the thermal decomposition, solvothermal approaches, and microwave approaches as like in a comparison. What gives you what? It's not about which is better. It's different techniques for different materials. And with this, I would like to thank you for your attention, and I would be happy to answer any questions.
Thank you, Eva. Oh, really nice. I have a question. Is a dinosaur is like a
Because it's a T-Rex and a non-nanorex. Maybe I have not to change into copy.
So we can questions. Okay, it's not bad. Questions, please. Frank.
Great talk, Eva. Why do you use fluorides always to make these particles? What is the role of the fluoride, and what would happen if you were to make oxides out of them?
You can make oxides, and for instance, gadolinium oxide, yttrium oxide, always the lanthanide 203 are very popular host material. I made them when I was a postdoc. The problem with them is they are more difficult to control in terms of morphology and size. When you go to the really small sizes, then they tend to agglomerate terribly. And also, another reason is because the FF transitions are forbidden and they are affected by the surroundings in terms of the lattice plays a role. And another aspect is phonon energy. So we have heard that earlier from Gael that he replaced all his H by F in order to match to have less match of the vibrational modes. In a similar way, the fluoride-based host materials have lower phonon energies than the oxides. That's why.
Yeah.
Sorry, I'll go into magnets because I know a little bit. So the choice of erbium was because that was what was available on.
No, there was more of that.
Or-
Yes,
yeah, okay.
yes. And also the cubic lattice was picked for the symmetry, and then the erbium was supposed to be a better match.
Yeah, okay.
And to be honest, the performance of the SMM is terrible. You cannot compare it to a molecular
Yeah,
one.
but it's like.
But it's the principle.
Principle.
Now I would like to see, do we use other lanthanides, other hosts, different architectures?
You just try to expose them around that.
No, nothing. So I need someone who has a script and is willing to spend a lot of time on it.
That's good.
Good.
All said.
Thank you, Eva. Congrats for your results. And just a question about the keeping agents like the fetal glycogen that you mentioned. Did you saw any optical effects on the really small particles concerning, for example, the difference of refractive indexes or some increase of some emission probability or even a lensing effect in this case?
We never looked into that. However, so when we compared ligand-free and PAA-coded and gamma-aerobic, we looked into the optical stability and how the emission intensity is affected by the ligand. There's definitely an effect on it. Not only the visible, also in the near-infrared, and also in terms of long-term stability. But I want to look a bit more into detail in that. I think it's a great idea to understand better what the ligand is doing, also for the nanothermometry. Because I think with the refraction index, it can have a huge effect on how light is reaching and getting on. To do.
Bem, questões dos alunos aí? Alguém quer perguntar? Não? So I have a question. When you measure the MRI relaxivity, I saw that you had you applied the magnetic field of 7.
Yes.
Did you try to decrease that? Did you study? I mean,
No, not for the.
align the
No.
magnetic.
They can't do a change of the magnetic field. We have the choice between 3 and 7. These are like actually clinical MRIs. We go to the hospital to do it. They can't change field. And because it's dysprosium, we opted for the 7, not for the 3 Tesla.
Because we are trying, we have nanoparticles with exposure, and we are injecting the racks, and we are not seeing any signal, but our instrumentation has 1 Tesla.
Oh, but maybe we can
Yeah.
test this another one.
Yeah, right now they couldn't get any signal from
Yeah.
disposal.
Yeah, I think dysprosium is well known to be more like the high
Yeah,
magnetic
yeah.
field one.
Questions? Okay, there is no more questions, so does this
One more question.
Okay.
What is the distance limit for the quenching between the inner lanthanide and the shell?
Yeah, so in our case, we could not rule it completely out. We probably would have to make it even thicker, but I'm not sure whether it would be possible, because now what really is happening, we have that erbium ions, they are not staying in the core, they start to leak into that undoped shell.
And also maybe the dysprosium ions start to leak. Yes, and we are trying to work with collaborators to understand whether this leaking across the nanoparticles is in the microwave actually worse than in thermal decomposition, or whether it is less, or whether it is the same. Because it's so much faster, maybe it's worse, but maybe also it's so much faster we don't give them time to migrate. So that's an open question.
Any questions? Thank you. Please join me. I'll have a break for lunchtime, and then we come back at 2 p.m. Okay? Nós voltamos às 2. Aí tem mais 2 seminários, o professor Frank e o professor Christopher. Aí o professor Frank vai para a energia, depois o professor Christopher provavelmente vai vir aí com moléculas e cristalografia. Então, obrigado, gente. Até a tarde.
Is it necessary to control the gas?
What we do is when we fill the solution in the vessel, we plug it with nitrogen. And then that's all. We use thermal decomposition. So we use the same degassing of our solution of the precursor
At the beginning.
at the beginning.
So
We
first
do
use a conventional sound bath,
exactly.
and then you
Yeah, you do the degassing under high temperature, then you transfer it into the vessel with ideally a little bit of nitrogen flow, and then you add a little bit of more,
I think that's
just for the transfer. You cap it. Not chewing the
because I work in Paris.
Yeah. Yeah.
And I actually read using this methodology, and I was thinking about if you use
Like tuning the reactor. No, actually it's a closed vessel, and what we need is to build up a little bit of pressure.
It's very interesting because you can get a very nice particle, and you can change some parameters, and you can get almost the same size and almost the same
So for the lanthanides and for the material where we figured out the protocol, it's very reproducible. It's very reliable. Of course, then there are some where it's totally.
Is it possible to go to the other side? You showed particles having 3 to 5 or 10 nanometers, and is it possible to go to the slider?
Not with the nucleic acid.
Yeah.
So
So maybe you can change the.
yes, yeah, I think so. And I think someone actually in Sao Paulo, they use polyacetylene or polyethylene glycol as solvent and water. Then typically it's a larger particle. Also the lithium yttrium large microparticles, we made them in a mix of water and hydrogen. But yeah, large particles are difficult with microwave.
I imagine. Because for some applications, it's good to have bigger
I totally
particles
agree.
because you increase the brightness.
Yeah.
And that's when you have bigger particles, you increase the
Even so, the particles are very small, they seem very bright, and measuring the quantum here, we need to measure.
You have
I do have an integrating sphere, but we still struggle with the setup. But in November, I will go I will be in her lab, and I will hopefully do the measures. Because they are so tiny and we are so bright they are.
And even in something, in water, it's
In
possible.
water it's lower, but in
But
chlorine,
you can see the direction.
yes, that's right. Yeah. But I have one student who really wants to see stocks, the sub-level and everything, so he makes big particles for some. What we also learn how to do is, because with thermal decomposition, you can make them small as well. Compare quantum yield out of the microwave and out of the thermal. Exactly. Yeah.
No bars there?
Yes, and also to understand how the microwave reaction actually works.
That's one of my leaders, is not to work only thermometry, but run through for.
Yes, yeah.
And that's something that I did very soon. And the idea is to change the golden particles.
Yeah.
Yeah.
Yeah, and there's like the size, it should not be too small, but not too
Yes,
large.
yes, yes.
Because if it's too large,
You're not, yeah, too large, you're not, there's no migration.
yes.
And but in that case, it's even better to use bigger particles because that's where you can put the CO2 mass
Yeah,
pressure.
yeah, exactly.
And
So
that's
it's
when
yeah,
it's a balance.
exactly. So, yeah, but that's where we sometimes, depending on the nanomaterial, if you have, I don't know, the core is maybe 6 nanometer, and then this one under the shell, it could be 3 nanometers.
We don't have because it's the best way to design the particle and the size of the shell.
The honest answer is trial and error. Good luck.
Because for example, if I have a core, active core, and then an inert shell.
Yes.
Sometimes I see that there if you have shell.
This, yes, but we tried this with the small nanoparticle and active shell.
Yeah.
It made it worse. And I think I saw one paper that actually reports that the active shell is not working on the very small scale, and it works much better on the larger scale. We also tried ones to do like undoped and shell. But maybe we have to retry again, because we tried this at an early stage when we were not so good yet. Maybe we have to revisit this. Yeah, there's a lot of things to play and try to control. It's a learning process. Yeah.
Thank you.
Thanks for the questions.
I figure then afterwards I get Gael, I upload your just take a picture of you.
Oh, okay.
But every is right there, so I do that.
Or we go in front of.
No, then I will take for each one with their own
Oh, I
presentation
have
and
to do
then,
that?
yeah, and then I.
Capybara. Cappy. Cappy and Cappy.
I see. My camera not.
Can we take one with mine?
Yeah, but I didn't take yet because I'm having thrown this people else. Yeah.
Oh, I don't know. Or
Then
I have to, you need my
those
face.
guys, yeah, my face will not work. You can't use your picture to open this.
No, yeah.
Unfortunately.
Thank you.
You upload yours now. Then
No, to run to the restroom.
well, I'm there for representing all these features. Here is working. No, she talk about this, but it's exactly aggregating particles. Yes, super.
Oh, yes. Yeah, like in the gadolinium oxysulfide or in the
No, it's
sodium?
with lithium batteries and fluorides as
Yes,
well.
yeah, although we need to talk what Gabrielle
So,
is
sure.
doing. You will be at Química, right?
Yeah.
Yes, yeah. Good. We have some more days.
No, it's not that much, but they come back on Saturday morning.
Okay. Good.
Thank you.
I will catch you.
We have some.
Yes. Are you also taking the 10:20 flight tomorrow?
No, it's slow. Well, but I'll be there.
Yes.
Tomorrow.
Yes. Yeah.
Is there any organization on particles inside the people like the shell?
We couldn't see that. Maybe we would need some much better TMs to be
No, but
able.
it's both.
Yeah, but in a high resolution, we should be able to see. Maybe these systems could also be nice for the particle to particle energy transfer. Because you force them together. And then it
For
would
lunch?
be easy to also
I-
do then
Can we
these
drop
like
back?
time changes
Yeah.
and yeah, and they, because they are relatively
Then
large,
see if I can
they are
find
easy
a
to
magnet.
probe in the microscope.
Yeah, you can even want
Yeah.
The unicorn
Yeah.
magnet.
Yeah, we are going there. Yeah, we are going to have lunch there.
That's what it's. What, you will join us?
No,
I'm having lunch here. Later. Leaving tomorrow.
Aqui.
Que hora
Que vai voltar?
as duas.
Ó.
Aí, nossa, tá pensando. A gente talvez seja melhor se deixar isso ficar, né? Desliga ele. Ah. Não, calma. Para sempre. Deve ter algum mas deixa só, deixa ele desligar, ele vai secar ainda mais. Não vai, né? Eu acho que estragar vai ser não.
Essa é uma coisa que para mim eu faço. Ah, ela vai parar. Yeah, but then all of the gases.
Oh, no, I tried deconvolution, but I forget about it.
Yeah.
Just hate with all the physical meaning.
Yeah.
Well, we have your.
Oh, I left it in the office. I can bring it.
You can bring us maybe? Do you remember do it? I mean,
Yeah.
you see that?
Yeah, I'll go get it.
Oh,
The pointer.
Do you remember the code?
Yeah.
Oh, wait for. Waiting for. This is so exciting.
Não sei, não sei. Faz parte eu acompanho a defesa de universidade, doutorado, não sei qual é. Mas é uma questão.
And I have 15 minutes. Thank you so much for coming.
In front of our lab, actually.
Thank you. Thank you.
Vocês podem levar o Frank lá. Tem essa de coisa. Né, mas é rápido, assim, Viu o negócio da bolsa lá? Lembrei disso hoje.
No final das
Bom, boa tarde a todos. Obrigado pela presença novamente. Então, só um recado. A gente está sem a maquininha do cartão, né? Eu vou passar a lista de novo. Por favor, vocês assinem e coloquem o RA, tá bom? Que aí depois a gente entrega lá na pós-graduação, tá bom? Okay, so let's start the afternoon section, the siesta section.
Yes.
And well, have a pleasure, a real pleasure to have here Professor Frank Osterloh from the University of California, Davis. Professor Frank Osterloh received his master and PhD degrees in 1994, the master, and 1997, the PhD from University of Oldenburg in Germany. And then he completed 3 years of postdoc training in Harvard University, Professor Richard Holm. In 2000, Professor Frank joined the faculty in the chemistry department at the University of California in Davis. His current research interests are centered on applications of inorganic materials for solar energy conversion. This includes the development of hot catalysts for hydrogen fuel generation via overall water splitting, artificial photosynthesis, the fabrication of inorganic photovoltaic devices, and the study of photochemical charge transfer reactions with surface voltage using the surface voltage spectroscopy. As of March 2024, Professor Frank was he has published more than 130 papers, 3 book chapters, and several review papers, articles. So, Professor Frank, thank you so much for coming all the way from Davis. Thank you so much. It's a pleasure to have you here, and the floor is yours, and everybody's excited to be here. Mario.
Thank you. Thank you so much, Fernando, for having me back here and being such a wonderful host. It's been a great time. And it's been 10 years since I met Fernando. He was actually in Davis giving a talk. And then a year later, he invited me to come down here. And this has had a really strong positive impact on my research program, as I'll show you in a second. So yeah, that's the title of my talk. That's my lab at UC Davis. We're supported by the National Science Foundation, which is one of the main science donor organizations in the United States, and the Department of Energy. I have 9 graduate students right now, but several of them are graduating. I happen to have Lucas Escaliante here. He's from Brazil, and Moises de Araujo. And they're supported by FAPES. And they're just 2 of the latest people that joined my lab. By the way, here's Davis. This is the Green Valley, the Central Valley, California, the Sierra Nevada, and here you have San Francisco and UC Berkeley. So we're just about 90 minutes away from the University of California, Berkeley. And as I mentioned, the fact that I came here in 2014 really opened the door for me working with a number of Brazilian researchers, and they're shown here. Mauricio Melo was one of my first postdocs, and he came from Ana Flavia Nogueira's group, and then also Saulo joined her, and then later Renato joined, and Hamilton, and Shirley, and as I mentioned, I have Lucas and Moises with me right now. And so thank you, Fernando, for making this possible, and also Ana Flavia, and then thank you, FAPEST, for supporting these researchers as they did research in my lab. So many of these people were motivated by doing something about climate change and by doing something about renewable energy. And we're seeing signs happening all over, the flooding, the terrible flooding in Porto Alegre just earlier this year, the wildfire smoke that is affecting us right now. So it is time to move on and switch away from fossil fuels to renewable alternatives. I don't want to scare you, but this is a little picture of all the wildfires that have happened in California just in the last 7 years or so. So in that time, 30% of the forest burned, and many people lost their homes. And let's hope that this won't happen in Brazil, but I don't know what's going to happen. Anyway, we need to do something about it. And but we're running out of time. If you look at carbon dioxide variations over 500,000 years here, they have never exceeded 300 ppm. But of course, in the last 200 years, due to burning of fossil fuels, we have rapidly increased that. This picture is probably from 2005 or so. So you see the peak is less than 400. But right now, does anybody know CO2 concentration in the atmosphere right now? 418, and by just 2050 we'll hit 500. So we can extrapolate what that will do to the temperature. So we're running out of time. We need to do something right now about it. And fortunately, we have a wonderful energy source that we owe our life to, and that is the sun. And the sun provides so much energy that we can power our entire society based on sunlight. The light that strikes the earth in just 1 hour provides that much energy, and that is nearly the same as what we used worldwide in terms of energy in 2001. So that's just 1 hour. So the question is, how do we tap into the solar energy? How do we harvest it? And then how do we store it so that we can use it? And that's been the central question. And inorganic materials are going to be a key material in order to achieve that, because they are stable and they can absorb sunlight. And many of you know about photovoltaic cells. What's a photovoltaic cell? Typically, that is a semiconductor that is interfaced with an electron selective material and a hole selective material. And then when you shine light on this material, long-lived electron and hole pairs are generated by band gap excitation of the semiconductor. And if these charge carriers are long-lived enough, then they can diffuse to these contacts and be harvested in the form of electrical energy. And we can calculate the efficiency of such a photovoltaic device by looking at the electric power output divided by how much light was absorbed, and that gives us the efficiency. And here's just a table of some semiconductors that have been used for photovoltaic cells. Over 80% of all commercial solar cells now that we can buy are based on silicon. And silicon solar cells have efficiencies now over 20%. Then other semiconductors are gallium arsenide, indium phosphide, copper, indium, gallium, selenide, and sulfide, cadmium telluride. These also achieve efficiencies over 20%. And right now, 85% of all solar cells are made in China. And so that's a question, will China be able to provide the rest of the world with this technology? And the other question is, can we do better? Can we raise the efficiencies further? So why not 100%? And of course, there are some limits, and I will talk about that briefly, what determines that. And but there's some room to improve there. Now, solar cells produce electricity you can use to charge a battery. but the solar cell plus the battery is very expensive. Right now, almost 90% of our energy that we consume is consumed in the form of fuels. So it would be best to turn this electricity into fuels. And the easiest way to do that is water electrolysis. We split water on the anode to form oxygen, and we reduce the protons to make hydrogen. That's a reaction that requires energy input to occur. Once we have the hydrogen, we can burn the hydrogen in air to get the energy back in the form of heat, or we can run the hydrogen through a fuel cell to get electricity out of that. So we use the hydrogen, basically we use the water as a battery to store electrons, and that's what hydrogen is. Hydrogen is a molecule that has stored electrons in it. And because we live in a world that has mostly oxygen, has a lot of oxygen in the atmosphere, we can use hydrogen as a fuel. A molecule that contains electrons is a fuel because those electrons can react with oxygen in a combustion reaction, and that releases energy. So that's, many people believe that hydrogen will be the fuel of the future because when you use it, you make hydrogen, you make water, so you close a cycle. Here we split the water, here we remake the water. No carbon dioxide emission, it's a clean cycle. So the easiest way to get to this right now is to simply combine an electrolyzer with a solar cell. And we recorded that little video a few years ago. Those are just some small silicon solar cells that we bought from Amazon. We wired them up, we connected them to 2 nickel electrodes, stuck them in the water that has a potassium carbonate as an electrolyte in it. Okay. You can see it's a solar energy fuel bomb. We made a little bomb there. And that shows you that we can store free energy in that hydrogen-oxygen mixture. This is, by the way, it's available on YouTube if you want to download it. So PV plus electrolyzer is probably our best hope right now to turn our society from a fossil fuel consuming society into a green energy society. There's a lot of work going on now, also in Anna Flavia's center, on battery, on fuel cells and on electrolyzers to make this electrolysis more efficient. And but long term, people believe, including me, that maybe we can also split water in a more direct way using so-called photocatalysts. And here's a picture of one of them. This has a semiconductor linked to a metal particle that could be an electrocatalyst. Under illumination, you generate the long-lived electron-hole pairs. Then the electrons separate into the co-catalyst where they reduce protons. And the holes, they are propelled into the liquid. This whole thing is immersed in water where they oxidize water. What you see here at that solid-liquid interface is called a solid-liquid junction. And such junctions were studied by Heinz Gerischer a long time ago. So this is how a photocatalyst separates charge carriers. And so this machine has to do a lot of functions at the same time. And you can imagine it's not that easy to design something that works well and that is also stable. Because we need to oxidize water here, we can only use semiconductors like oxides and some nitrides that are chemically stable against the self-oxidation reaction there. Now, well, it turns out, and that was a surprise to me when I found out about it, that most of all photosynthesis on our planet, the conversion of solar energy into reduced carbon and oxygen, is actually performed by particles, by phytoplankton particles that drift in the oceans, and they are known as phytoplankton, and they have large blooms. Here's one. They're basically the bottom of the food chain of all life in the oceans. And there is fixed carbon. So I do believe what we need is, we need an artificial photosynthesis of fuels that we also do on a global scale, just like these photocatalysts. And until a few years ago, namely 2013, it was actually believed that these photocatalysts for overall water splitting can be cheaper than photovoltaics and electrolyzers. So this is the calculated price from this analysis here for a photovoltaic electrolyzer system. And you say, you can see it costs about $10 per kilogram of hydrogen from that. Compare that to a photocatalyst system, that's only 1/10 the price. Now this analysis has changed a little bit because the price of photovoltaic energy continuously decreases. This is a logarithmic scale, by the way, here. So every couple of years, as more photovoltaic panels are being produced, solar energy and solar electricity becomes cheaper and cheaper. And for that reason, probably right now, the PV electrolyzer configuration is the best way to go. But anyway, in my talk, I mostly want to talk about photocatalysts because I can use this to explain some of the fundamental principles that you need to know about when you want to turn sunlight into fuels. So that's what my talk is going to be about. And there have been some very positive developments, mostly by the group of Kazunari Doman in Japan, who has worked on this for 40 years. He has published this aluminum-doped strontium titanium oxide photocatalyst sheet. Those are basically thin films of this material under a plexiglass and in contact with about 1 millimeter of water. And when you shine light on it, hydrogen and oxygen just bubbles out at an energy efficiency of 0.4%. And I'll come back to this catalyst in a little bit. Then his lab also published this one. This is actually the record holder right now. This is a lanthanum rhodium co-doped strontium titanium oxide particle in contact with bismuth vanadium oxide molybdenum dope. And this is all printed on a gold surface and connected electrically with gold. And you just saw that little video. That was what happens when you illuminate that sheet with light, and then these hydrogen oxygen bubbles come out. So this is the record right now, 1% solar to hydrogen efficiency. So I have to take that back. This is actually the record. This is the record. Indium gallium nitride nanowires produced by electron beam deposition on a silicon wafer. This is work from Zetian He's laboratory at the University of Michigan. And under 160 suns, so there's this concentrated sunlight, this evolves hydrogen oxygen bubbles. And here's some ideas about the charge separation mechanism. The electrons are used to reduce protons and the holes to oxidize water. And for some reason, this gallium nitride is very stable against corrosion, and this is why this works relatively well. The drawback is indium is expensive, gallium is expensive, the fabrication method is expensive, so this is not a scalable technology right now. Well, let me give you some more examples of overall water splitting catalysts. It turns out there are not that many. Here's an example of a single absorber configuration that may have a co-catalyst for water oxidation on it, a co-catalyst for water reduction, and then the light absorber. And there's only about 13 examples of this in the literature that can operate under visible light. And most of these were developed in Japan, and we just got a number of names. Then we have a few examples of where we have separate hydrogen evolving particles and oxygen evolving particles in a so-called tandem or Z-scheme configuration. So they both get photoexcited and they transfer some charge carriers to achieve the overall reaction. And using two particles allows you to use smaller band gaps, and you can absorb more sunlight that way. And then there's another configuration of that uses a soluble redox shuttle that could be something like iron 2, iron 3 or so in solution that shuttles the charge carriers back and forth. So if you count that, that's less than 50 examples. But then if you look at the literature, what you'll find is there are probably 50,000 papers on photocatalysts. And so why do we have so many papers on photocatalysts when there's only so few water splitting catalysts? The reason is that most papers on photocatalysts actually cheat a little bit. What they do is they use catalysts that turn water and some added chemical reagent like methanol or amines into hydrogen products. And because you add these additional molecules, it changes the thermodynamics of the forward process to make a product that is thermodynamically more stable than the starting material, so it's thermodynamically downhill. And there, the light merely helps to fasten the reaction. If you truly want to store light energy in the products, then your products need to be thermodynamically, need to have more free energy than the starting materials, and then the light is used to both promote the reaction rate and also deposit energy in the product. And so I wrote a paper about that a few years ago, and so people like Alan Ward, for example, in the United States, they call this photosynthesis and this photocatalysis, depending on the energetics. Now, making your system go uphill is really difficult because when you arrive on the product side, what prevents your system to just catalyze the back reaction? Like hydrogen plus oxygen gives water. That reaction is thermodynamically favorable, so there's a huge driving force for that to occur. So in order to prevent that, you need to engineer your catalyst in a specific way, and I'll talk about that in a little bit. So that's why there are so few overall water splitting systems known. Now, what can we do to build such catalysts, and what can we do to improve them? That's what I want to talk about a little bit. And so we need to concern ourselves with the primary events in photocatalysis and photosynthesis. Here's a particle of a semiconductor. This is actually modeled after a tungsten oxide particle that we imaged once with SEM. And now we expose this to light. The semiconductor gets excited to make electrons and holes, and they can have various lifetimes. Then the next thing is we need to separate them. If we don't separate these charge carriers, they will just recombine, and then the energy goes away as heat. And so we need to transport the carriers to the surface and separate them from each other. Then we need to use them to reduce protons, that's an electrochemical reaction, and to oxidize water, that's also an electrochemical reaction. And these processes are pretty slow. And then additionally, we need to engineer this thing so that the electrons and holes cannot recombine with each other, and that the oxygen that is generated here cannot go here and be reduced back to water. That's the back reaction. Those are the things that we have to do. And the challenge really in all of this is the different time scales. You know, the absorption of the photons and the generation of electron hole gases, this happens on the femtosecond time scale. Then the transport is several orders of magnitude slower. And the water oxidation reaction occurs on the order of seconds. So that means you really need to have an efficient charge separation mechanism, because otherwise the holes that form here, they would just recombine and your energy is lost. So let's talk about some key parameters that we need to optimize here. One of the first important one is the band gap. The band gap tells you the difference between the conduction band edge and the valence band edge in a semiconductor. That's like the LUMO in a molecule and the HOMO in a molecule. The larger the band gap is, the more energy of the electron hole pair that is generated under illumination. Now, if we want to turn sunlight into fuel, we need to make sure that our semiconductor can absorb the sunlight. And it turns out a semiconductor can only absorb photons that have an energy equal to or larger than the band gap. So in this case, this is a 2 eV band gap, and that means it can only absorb photons with wavelengths smaller than 620 nanometers. Now, let's look at the solar spectrum. This is the solar flux. This is the number of photons per square meter, per nanometer, and per second. I forgot that here. And so this is how it looks like. So most of the solar energy is in the visible region here, a little bit is in the UV, and a lot of it is in the infrared. And then if you take all these photons and you integrate up to over the entire wavelength range to go to 100%, then we can take the 620 nanometers here and plug that in, and then we automatically see that if our catalyst has a 2-point EV band gap, it can only absorb photons in this region here, and that's only going to be 24% of the total. That immediately determines that your efficiency can never be higher than 25% if you use a 2EV semiconductor. Now, you could use a smaller semiconductor with a smaller band gap, then you would absorb more photons, but at the same time, the energy that is stored will be less because the band gap also determines the energy. So very briefly, if you were to plot the efficiency of electric power output versus the band gap, you kind of get this kind of curve where you get the maximum at about 33% for a 1.2 EV band gap. And if your band gap is larger than that, then your efficiency goes down. When the band gap is larger than that, the efficiency goes down because a large band gap semiconductor cannot absorb most of the photons. This is also shown in this diagram here. So this curve is this black region, that's the usable electric power. As we go band gap up, we have more and more photons below the band gap that we can never absorb, so that's a loss. On the other hand, if we make our band gap smaller and smaller, what happens is that the charge carriers that are absorbed, they are absorbed, let's say, at 3 eV, but they relax to the band edges, and we have an energy loss there. And that's then the loss term here. And then we have some other losses from separating the charge carriers, but now overall, this is the curve. This is why we can't have 100% solar energy conversion efficiency with a single absorber. This is known as the famous Shockley-Queisser limit. And that also applies to water splitting photocatalysts. Now, there's another thing very important, and that is the optical absorption coefficient. So that basically tells us how strongly does a material absorb light at some wavelength. And let me illustrate that here with these diagrams. So basically what we have here is we have the energy of the states in the semiconductor, and then on the right side we have the density of states. So the density of states is basically how many orbitals are there in your crystal that can be occupied with charge carriers, and then how many orbitals do we have here that are empty. It's easy to see if you have a lot of orbitals, and if you excite this with some energy, there's many pathways for excitation, and that means the absorption coefficient of this material will be very large. On the other hand, if you have the situation on the left side, then you, at the same wavelength, you absorb a lot less. That means you need a lot more material in order to fully absorb the light. Now, we can measure that using absorption spectroscopy. You're all familiar with that. Now, for materials, we don't have solutions, but we just use thin films. And that means for a material, the absorbance is determined by this law here. We just have the absorption coefficient alpha, and then we have the length of your material, the thickness of your film to relate to the absorbance. So the thicker the film, for a given absorption coefficient, the better the absorption. Now, here's some absorption coefficients for different materials. Silicon 10 to the 4 per centimeter at 500 nanometers. Bismuth vanadate, that's a popular water oxidation material, has better absorption there at 460. Gallium arsenide has even better absorption. As a guide, you can say the more more lightweight your material is, the more atoms there are in the unit cell, the more states you have, and the better your absorption coefficient. Why is this important? Well, it's because the absorption coefficient determines the light penetration depth. The light penetration depth is just 1 over alpha, so 1 over the absorption coefficient. and it gives you directly the percentage, the distance over which 63% of the incident light is absorbed. So if I have a particle like that, that is about, has a diameter of 2 times of 1 over alpha, then for that one, I would absorb about 90% of the light in that one particle. And so the less material you need to absorb all the photons, the better, because then your charge carriers are a lot more concentrated. Now, here's a picture of some bismuth vanadate films, and you can clearly see if your film is too thin, you can almost look through, but the thicker portions, they absorb more, and that's what we need in this case to absorb all the light. Okay, well, here's another important variable, and that is the so-called charge carrier diffusion length. Once we absorb the charge carriers, we need to get them out of the material. And we can use the mean free diffusion length to see how far these charge carriers can travel. And it's simply the product of the diffusion coefficient of your charge carrier and the lifetime of your charge carrier. So the larger the lifetime, the longer you can transport these charge carriers. Now, you can have different diffusion lengths for the electrons and the holes. Like in an N-type semiconductor, often the hole diffusion length is smaller than the electron diffusion length. And so picture 2 particles of the same material, or of the same material. So if I excite this one, then these carriers in the center, they will never be able to come to the surface because the particle is larger than the diffusion length of the charge carriers. In order to get all the carriers out, I need to make the particle smaller. If I make the particle smaller, then they have enough time to diffuse out. And that means that with size, you can often control solar energy conversion and photocatalytic activity. Here are some values for the same semiconductors as before. So silicon has very long diffusion length. These carriers, they can move a long time, and other materials don't have that. So for bismuth vanadate, to make a good photocatalyst or solar energy converter, you need to nanoscale the particle for optimal charge extraction. This is actually something that we observed a while ago, where we investigated photocatalysis with tungsten oxide. We take tungsten oxide particles like this one, we mix it with water, we put a little bit of a little bit of iodate in there, that's a strong oxidizer. We shine light on it, the electrons go to the oxidizer, the holes accumulate and eventually oxidize water to make O2. And then we can measure the O2 over time and compare the activity by looking at the rates. And what we find is that the large particles here, they have the lowest activity. Then these plates that are intermediate in size, they have an intermediate activity. And the nanoparticles, they have the highest activity. And that clearly shows us that the activity here is transport limited by those carriers. And the best system is the nanoscale system. Now, in order to do such measurements correctly, you really need to have what we call a closed loop illumination system, where you have copper wires like this here that hardwire your reactor to the gas chromatograph. We use a gas chromatograph to detect these gases. If you do not have a closed system, then you will always have air contamination, and then you can never detect oxygen properly. So that's a danger, that a problem that people run into. Even Michael Gretzel in the 70s, he did some of the first water splitting systems. He claimed you can split water with cadmium sulfide illumination. And that was only because his system was contaminated with oxygen from air. He never retracted the paper, he never apologized for it, but it's common knowledge that this was wrong. And he published a couple more papers like that. So even if you're really smart, you make mistakes, and but people forgive you, I guess. Anyway, now saying all that, I think it's also important to know what the so-called photovoltage is. The photovoltage is the measure of the free energy that you can extract from an illuminated semiconductor. In order to split water, we need to generate a voltage of at least 1.23 volts in order to drive the proton reduction and the water oxidation. This photovoltage can be calculated on the basis of the positions of the conduction band and valence band, and it is very much strongly a function of the steady state concentration of your electrons and holes. So in order to get a photovoltage like 1.23 volts here, what you need to have is you need to have a large steady state concentration of these charge carriers, and then you can split water. And we can, for a large concentration of electrons, we can even assign an electrochemical potential to the reducing power. We call that the quasi-Fermi level of the electrons. And we can assign an electrochemical potential to the holes. That's the quasi-Fermi level of the holes. And the difference between the two is then the photovoltage. So in this way, an illuminated semiconductor is very much like a battery that also has a voltage. And the voltage is in volts. And if you multiply that with the charge of an electron, then you get an energy. And that's pretty much free energy that you generate with your illuminated semiconductor. So this is one of the key variables that determines efficiency. Well, what are the problems that we have? Well, one of the biggest problems in all these materials is the fast electron-hole recombination. And so electrons and holes do want to recombine. There's a huge thermodynamic driving force for that. And this can occur in various ways. One way is, let's say you have a defect in your band gap, then the electrons are attracted to it, the holes are attracted to it, and they will recombine. We call that the Shockley-Reed-Hall recombination. Such defects also exist at the surface. At the surface of a crystal, you often have dangling bonds and a transition from a crystal into liquid. And so these intermediate states exist and they attract both electrons and holes, and they will lead to loss of your free energy. And then in addition, of course, we also have radiative recombination. If you didn't have any of these defects here, eventually the electrons and holes would radiatively recombine, and we saw some examples of this earlier today. That is just the phosphorescence or luminescence. So a material that has a phosphorescence or a luminescence, you can automatically see has few defects, that material, and would be a great photovoltaic material or a great photocatalyst material. And there's this complicated equation here. Basically what that means is that so this is the total lifetime of the carriers, and we can calculate it on the basis of the lifetimes limited by radiative recombination, defect recombination, surface recombination. I'm not going to talk about this right now. And so it turns out many of the photocatalyst materials that people have studied recently have very short lifetimes. Compare that with main group element semiconductors, they have very long lifetimes. So these can convert sunlight into electricity much better than things like hematite. That's the principal problem in this material. Well, let me show you an example of a case where we were able to optimize the recombination, and this is the famous strontium titanium oxide catalyst that's been known since the 80s. Was discovered by Doman, and more recently it was discovered if you synthesize this material under certain conditions, then its activity can be drastically enhanced. So my student Sid Chong, who graduated in 2019, was able to do this study. She synthesized the material. We start with strontium carbonate, titanium oxide, heat that to 1,000 degrees, then you get the strontium titanate out of it, this is white powder. And then, in order to get the active material, this needs to be mixed with strontium chloride and heated to 1,100 degrees. Under those conditions, this all melts, and you get a solution which dissolves this and recrystallizes it to make the product. Now, this product is also doped with a little bit of aluminum because this all has to be done in an alumina crucible. The particles, as a result of the crystallization, form really nice facets. They form little cubes because that's the perovskite crystal structure that makes cubes. Now, to make this a water splitting photocatalyst, we have to put a proton reduction co-catalyst on the surface. And we can do that by mixing this with rhodium chloride, chromium nitrate, and water, evaporating the water, annealing at 350 in air. And then on the surface, you get this rhodium chromium oxide that is the proton reduction catalyst. It's a very special proton reduction catalyst. It is one that can reduce protons as needed, but it also has the ability to prevent oxygen reduction. If you have oxygen around, the oxygen cannot go to the core of this material and accept electrons. It is blocked at the surface through the lattice of the rhodium chromium oxide. And this is a key invention to block the back reaction. If you did not do that, then you would always have the thermodynamically favorable back reaction occur. That is the case with platinum, for example. So now, you put this catalyst in water, you leave it out in the sun, and that's an experiment we did, and you come back after 6 hours, and then you can calculate the energy conversion efficiency. It's very small, but it works in a catalytic way. You can do it over and over again. You can also take this catalyst and illuminate it with about 3 suns, 320 milliwatts of light from a xenon lamp, and then now we evolve millimoles of hydrogen and oxygen there. So after 5 hours, you get 200 milliliters of gas. And that's when it gets really dangerous, because when you make so much hydrogen and oxygen gas in a glass reactor, you've got to be careful that it won't explode, because if it does explode, it'll smash everything. So the efficiency of this can also be calculated with this quantum efficiency. That's how many photons actually make hydrogen, and the efficiency is 15%. Compare that to the version without the aluminum, the old one. There the efficiency is much, much lower than that. So our task was to find out, why does this aluminum doping enhance the activity so much? And one clue was provided by Yamakata in Japan with that transient absorption spectroscopy on this catalyst, where they excite the catalyst, and then they look at the optical signature of the photoelectrons and photoholes over time. And normally, those electron hole concentrations diminish very quickly, as shown here for the as purchased material. But when you make this in the aluminum crucible, then the lifetime is much longer due to the aluminum in that material. So why does the aluminum make this so much better? And the solution to that was provided by Renato Goncalves in Sao Paulo, Institute of Physics. He did XPS on the strontium titanium oxide and the aluminum doped version, and they both look pretty similar, except this one here has a little bit of, has mostly titanium 4 in it, as expected from the formula, but then it has a small titanium 3 population. You can see that with these 2 lines. Once you put the aluminum in, that goes away. So where does this titanium 3 come from? Well, the titanium 3 is a byproduct of oxygen vacancies. When you take oxide in general and you heat it in air or in vacuum, then a little bit of the oxide just evaporates and becomes oxygen and gets oxidized. And that's shown here. And the electrons that belonged to the O2 minus, they stay behind, and they reduce some of the titanium 4 to titanium 3. So this is why most metal oxides are N-type semiconductors, because they have a small reduced metal concentration in it. This always happens when you heat up a metal oxide. Now, if we put aluminum in the mix, then the aluminum is Al3+, and it happens to fit on the titanium 3+ spot, and it can replace all the titanium 3+ with aluminum, and now we have no more titanium 3+ in the material. Now, this has a really positive effect, as we could confirm with Muhammad Huda based on density functional theory calculations. This is the density of state in the valence band and in the conduction band of the material. Sorry, actually, it might be the other way. No, that's right. And you see there are no states in the band gap as expected. Once you have oxygen vacancies, you get this titanium 3 population. So it's a new state in the band gap. And this state is banned for recombination. Once you put aluminum in it, it clears it out, no more recombination. And this is how this works. So basically, by putting aluminum in the material, we are eliminating these effects, and now all the electron hole pairs are available for water splitting, and the lifetime is drastically enhanced. We call this the adiabatic doping strategy, and I think it's a general strategy that can be used to improve metal oxides for solar energy conversion, and we're working on that right now. Now, that's not the only reason why these particles work better. The other reason is that they have very smooth facets. Smooth facets mean that the specific surface area is small, and that means that we have fewer surface states that can be recombination centers. So you want to make nice facets for them. There's another reason why facets are good, and in order to explain that, I have to briefly go and introduce what a junction is. So the solid-liquid junction. This is a semiconductor with a conduction band and the valence band, and we have a metal contact on the backside. This is the Fermi level. That is the electrochemical potential of your metal. That's basically how reducing your semiconductors. When you put this in contact with the liquid, the Fermi level. When you put this in contact with the liquid, what happens is some of the electrons from the material, they go into the liquid. And because the liquid may contain other species like protons and oxygen, they can be electron acceptors. And then what happens is you form an electric double layer at that interface. Now you have the electrons here, some are given to the hydrogen and the water, and we have holes in here. And now we have an electric double layer, and when you have that, you have a variation of the electric potential inside. And that causes this band bending, and it leads to a potential barrier. And this potential barrier is a key signature of a junction force. Now, if you have such a barrier, if you have such a junction, when you shine light on this thing to make electrons and holes, some of these electrons, they see the electrons out here, they feel that electric potential, and they are repelled from the interface and promoted into the interior. On the other hand, the photo holes, they are moved in this direction because they see the electrons, and that moves them this way. This is the reason why solid-liquid junctions can separate charge pairs. This is the reason why any of this works in the first place. Without a junction, you don't have energy conversion. Without a junction, you don't have charge carrier separation. So what we found out is, this is when you illuminate this some more and you form lots of electrons and lots of holes, then eventually the potential barrier goes away. You harvest the holes here at some potential, you harvest the electrons here at a different potential, and you get a photovoltage now. That's the illuminated junction. So what my student Sam found about 2 years ago is that the junctions that form at semiconductor facets depend on the facet. And that's actually not too difficult to understand, because if you take a crystal and you cut it in different directions, as shown here, these are the Miller indices for lattice planes in this material, then each facet here has a different chemical composition. They have different chemical compositions. And of course, if the chemical composition is different, then we would expect that also the energetics at the surface are different, and we would expect different junctions. And indeed, he gets a variation between these of about 0.16 electron volts between these facets. And because of that, if he uses these crystals to do water splitting and measure the photocurrent as a function of the applied potential, you can see that the crystals with the best junctions, they make the highest photocurrent, and the crystals with the weakest junctions, they make the worst photocurrent. So this really controls the charge separation and also the water oxidation rate. And this was a really important discovery because the fact that different facets have different junctions was already speculated a little bit earlier by the Doman lab to explain the high efficiency of their aluminum doped strontium titanate crystal. They say that these facets here attract the electrons and these ones the holes, and they did some simulations that predicted if you have a junction difference of 0.2 eV energy difference, then one can be hole selected and one can be electron selected. So we were very happy that we were able to prove that in our system. Also, we recently published another paper on gallium phosphide as a photocatalyst, and this is a main group element semiconductor, a very simple structure, has a small band gap, absorbs visible light strongly, and we wanted to see what does it take to turn this into a good hydrogen evolution catalyst. We took the wafers, we ground them up into particles, and then we illuminated them, and we measured the hydrogen. And one thing we saw is that if we took the crystals and etched them before, then we get more hydrogen out than the non-etched particles. Now, of course, we know to make a good photocatalyst for hydrogen evolution, you also need to have a co-catalyst. And so we put either platinum or rhodium chromium oxide or dinickel phosphide on the surface. And indeed, what we find is that we get much larger hydrogen evolution. Always for the etched produces much more than the non-etched, and the reactivity order is in this direction. And in order to understand that, we used other methods. I don't have time to talk about it, but we were able to see that the etching removes these surface states that are recombination centers, and this is why the activity is boosted. And then as far as the co-catalysts are concerned, here we found that the different co-catalysts have different Fermi energies, and they make different kinds of junctions with the semiconductor. And dinickel phosphide is the best, because for dinickel phosphide, this barrier here is the weakest that makes an ohmic contact, and then the electrons can go into the dinickel phosphide. If you put platinum here that has a very oxidizing work function, you get a junction that repels electrons. So the electrons can't go to the platinum, and that limits the performance. We also studied the dependence of different reducing agents on the performance for hydrogen evolution. And when we tabulate the electrochemical potentials of these donors here versus the hydrogen evolution rate, you can see that there's a trend. And we can very well understand that in terms of a Gibbs-free energy relationship, which predicts that the more difficult a reaction is, the larger the activation barrier. So a more difficult reaction is slower. And that's in fact what we find here. So if we use iron 2, then we get a slow reaction rate because iron 2 is the most difficult to oxidize. On the other hand, sulfide is the easiest to oxidize, and we get the highest rate. And we were able to exploit that to make a record efficiency by simply illuminating our catalyst in the presence of sodium sulfide. If everything's optimized, then we get now 15% quantum efficiency. So many photons make hydrogen, and we were very happy with this. This is about 500 times better than what anybody had done before. We also did this a while ago, not with N-type gallium phosphide, but with P-type gallium phosphide, and we found much lower activities there. Look at the units of 50 micromoles compared to 1,000 micromoles there. And the reason is that in a P-type semiconductor, the junction has the opposite polarity as for an N-type semiconductor. In an N-type semiconductor, the holes come out to oxidize the donor. In a P-type semiconductor, the electrons come out to reduce the donor. That's the opposite polarity, and so for that reason, this doesn't work at all. And so this explains why most photocatalysts in the literature are based on N-type semiconductors. I think I'm running out of time, so I want to skip this here. This is about ferroelectric effects. If you're interested, the paper is published there. And I just want to summarize that we need certain attributes for solar energy conversion. We need to have band gaps that fit the solar spectrum. We want to have long-lived carriers. We want to have high absorption coefficients. We want to have good facets for improved charge separation. We want to have well-defined junctions. We want few defects. And then I didn't talk about that, but you're welcome to look it up. Thank you so much for your kind attention.
So the second is open for questions.
Lovely talk, Frank. It took copious notes. It felt the lessons were sound. Slide 35, I had this is when you doped with the aluminum, to make the I3 plus defects go away. What I didn't understand though is it felt a little chicken or the egg to me, because wouldn't the O2 still form anyway, owing to that evaporation comment?
Yeah, you mean this one, the O2? Yes, it still forms. We still have the oxygen vacancies, as you can see, O3 minus X. But so the titanium 3 has to form here to compensate the loss of oxygen here, as a charge compensation. Now, we can achieve that by simply doping aluminum 3 plus in it. Then the charge is balanced here, and the titanium is no longer in the mix. Now, I didn't talk about this, but aluminum, of course, does not have d orbitals like titanium that would cause this state here. The aluminum states, aluminum is in the lattice, but the aluminum states are all in the conduction band, and there are no obstacle there.
Gotcha.
Okay.
That was
your question?
You took that from my question.
Oh, I'm sorry. And one quick follow-up, if you don't mind, on 45 and 46, you were talking about the different facets of the prostate phase. How did you promote one over the other in the synthesis?
That's a very good question. I think you would have to grow these crystals in a flux, and then that's an art for itself. But we know that if, for example, let's say you grow this in a flux, it could be that you might find certain metal ions that like to absorb to the 110 facet, and then they will stop the growth there. They can be growth inhibitors. And if that was the case, then the crystal would grow along 100 more, and you would end up with crystals that are mostly terminated by 110. So that's nanocrystal shape engineering. There's a lot of...
You did that though, right, in order to get data that was...
Well, this is a microcrystal, or...
But you had potential versus facet.
Oh, no,
we
we just bought commercial crystals. They're single crystals with these different orientations. It costs about $100 per square centimeter.
You have a lot of Excels in here.
Fred, thank you for this really amazing talk. So my question is, like, when you're using your foot catheter, hoping that you're actually more than one sun, because you really want to speed up the formation of hydrogen, but also you're forming oxygen. So this is could be like a silly question, but do we have a limit for generating like oxygen and hydrogen together? Because I'm really thinking about scaling this. And of course, you want to generate more hydrogen, but also you're generating. So this is something we were discussing yesterday. So maybe using like biomed instead of like producing oxygen, using other, because that's something else would be like a way to go. Because I'm just thinking about scaling this.
Yeah, that's a very good question. And Kazunari Doman asked that question a while ago with his system. And he demonstrated that if you make your reaction space here very small, it's only like a millimeter of gas space, then even if you were to ignite this mixture, there would be no explosion to destroy your reactor. And then he even demonstrated if you pipe the hydrogen-oxygen mixture through a polyvinyl chloride rubber pipe, and if the diameter of the pipe is no bigger than, let's say, 2 millimeters or so, even if you set that on fire deliberately, the explosion is going to be very limited and will not cause any problems. But then, of course, once you have your hydrogen mixture, then you need to start separating it. And so what they do is they use a semi-permeable membrane that where the hydrogen can go through, and then you can harvest it at 1 ATM and put it in a cylinder. And then you have to reject most of the oxygen, and it'll just go into the air. So that's an additional energy expenditure, this separation. And so this is a problem that people have not really studied a lot. There are no good engineering solutions for it, but it's Not, there's no, conceptually, it's possible to do that with low energy input. That's a very good question. Thank you.
Eva?
Thanks. I think I learned a lot, but I have some questions that are related to the ones Chris asked before. So when you dope the aluminum, it's not the interest to avoid the oxygen vacancy.
No.
You want to avoid the titanium 3+.
Yes.
And then do you optimize the amount of aluminum that you are adding in to optimize performance? Does dopant rate play a role?
Yeah, so 1% is typically very good, and it doesn't just work with aluminum. You can also restore the charge balance in this system by replacing the strontium. So if you can replace some of the strontium with sodium ion, and that will also restore the charge balance here. And so there are many dopants that work, and we call those adiovalent dopants. They're called adiovalent dopants because they have a different charge than the metal in the host lattice. So here it's aluminum 3 versus titanium 4, or it would be sodium 1 against strontium 2. And I do believe that this is a general strategy to deal with this problem broadly.
So if you don't have enough, you still have your titanium 3+. If you have too much, it doesn't help anymore.
Yeah, too much doesn't help anymore, but it also doesn't kill your system. So.
And then as you're just having this, like here with your ruthenium catalyst, you showed some images where you also show that this is a good one because it prevents the reduction of the oxygen.
Yeah.
And looking at the SEMT images here, this one, it doesn't look like it's really a dense shell around your.
Yeah, it's an oxide. This is actually the second generation. The first generation was rhodium with a chromium oxide shell, and this is when they drew this picture. So the chromium oxide shell is also shown here. That's like a molecular sieve that allows hydrogen to diffuse through, but it does not allow oxygen to diffuse through. And so it's a molecular sieving effect. And somehow the same effect works here. I think maybe when this one is active, I could imagine that some of the rhodium nearby gets actually reduced to rhodium 0, and then you still have a chromium-rich surface around it. So the two are not identical, but they function the same way. So this co-catalyst is the key for all overall water splitting systems. Without this catalyst, most won't work. So there's a tremendous challenge. Come up with some other selective proton reduction electrocatalysts, preferably some that don't have rhodium in them. And that would be great.
Question over here.
The last water presentation, I had read some of your previous science documentation.
Thank you.
I had a question first about the amount of aluminum. So there is no relation with the properties of the aluminum oxide in split the water. So
Yes, that
the
is.
report properties of the aluminum oxide split the water.
Well, as you can see here, those are two different crystals. Some have more aluminum and this has less aluminum in it. So the amount of aluminum matters. So it gets better as your aluminum increases. And then if you put more, it does not get worse. Or maybe it gets a little worse, but yeah, the amount matters, the concentration matters, yes.
The other question is, have you ever tried to oxidize the water into hydrogen peroxide?
Not deliberately, but we published one paper where we used a niobium oxide. That was about 14 years ago, and that one makes mostly H2O2, not oxygen gas, just H2O2. Also, titanium dioxide, when you excite that, also makes a lot of H2O2. Yeah, H2O2 is a value chemical. If you can make a lot of it, you could sell it.
That's the reason to become the overall process more profitable.
Yes.
Any other question? Over here.
Okay, thank you. I followed your presentation
the main force behind is a junction, which is the junction voltage to the solid and liquid. Now I was wondering if your catalyst is a homogeneous catalyst in a solution. Is it possible to have that junction?
Probably not, because in order to have a junction, you need to have an electric double layer, and that means it has to have a certain size. Molecules can still separate charge, but they will have to use kinetics to do it. You know, maybe you have one side on your molecular catalyst that just is very fast at transferring electrons to a proton, and then you have another part in your molecule that's just very fast at delivering holes to some. So it's the kinetics that control the charge separation.
One more question? Anthony?
Sorry, like this is a materials question or material synthesis question. The facets, you talked a lot about, and of course facets are very important in the activity, but also your samples seem to be very heterogeneous in terms of size distribution.
Yes.
Do you think there's room for improvement if this would be a more homogeneous size control on this?
Yeah, as I mentioned, to extract the carriers and also absorb all of the light, there's a sweet spot in terms of size. And so if you can make particles at a specific size, that could optimize the performance.
There's nobody doing this in the work?
Maybe some people, but I don't think it's not, this is a new, I think this is a new direction. Thank you so much. I also want to mention, I'm going to be sending a PDF of this to Fernando, and then anybody who wants that, you can have a PDF of my presentation of them. I hope that's okay with you, Fernando.
No problem. It would be an honor. Basically, if you want, if you like to have Professor Frank's presentation, the slide, is that?
I'll make a PDF.
The PDF. Yeah. Then you'll send an email to me, and I send you back to the PDF.
Thank you.
Okay. So please join me, and thanks. Eu espero que esteja com o break, ele não pegou ainda mais. Né? E às 16 horas a gente retorna com a apresentação do professor Luiz.
It's not here yet, so. Yeah. You are the boss.
A senhora vai estar aqui?
Não, eu vou levar o Frank.
Então. Não.
A lista de presença está